Okay, whenever want to start, I can. Okay, whenever Peter, you want to start, and I can start it, right?
One moment, we are starting recording. You can start.
Timothy, I can't hear you. Are you talking?
Okay, I'm talking now.
Hear me? You can start.
Yeah.
Anytime. You can begin.
Am I go first or who go first? Peter?
Or
Can you hear me? Hello?
yeah.
I'm here and ready. You hear me?
Yeah. Go ahead.
Okay, everybody, I'm going to make this as short as I can. Okay, because if you let me go on, I can talk for many hours. Okay, this is one of my exciting project when I was very young, and when I was encounter the fourth language and doing the Chinese computing at the same time. Okay, so my talk is the Chinese fourth and computing. Actually, there is something to do with F83, but let me kind of bring up a little bit on my encounter with force, because at that time I need to find a back to 1980s, the personal computer just started, and I need at the same time I need to find a way to build a Chinese typewriter so that I can write more legible and my mom won't get upset. Okay, my mom was a school teacher and she feels ashamed that her own son cannot write nice. Okay, so that's why I started, and then I wrote a couple of books in Chinese, which the cover is shown on the upper left and the lower right. Okay, so that time I was thinking that what American people write very terrible. Their handwriting most of the time I couldn't understand. I couldn't read it, but at least in the States there's a computer, a typewriter, and the secretary would type whatever, and nobody had problem of reading it. But for Chinese, there was no such a thing. A famous Chinese scholar, Lin Yutang, he spent all his savings, but finally failed to make a good Chinese typewriter. And in 1974, Intel started producing the 4004 chips, and then 8008, and then 8086, that kind of computer. So at that time, I thought, well, computer is no longer an issue of, it used to be millions or a couple 100,000 in order to get a mini computers. But, with the microprocessor coming out, personal computing won't be, the price of personal computing won't be a prohibitive factor. So then, I find out there is a FORTH interest group and can download the fake FORTH. So I start with that. And also by chance, met Chuck Moore, the inventor of the FORTH. And then when Kim Harris, have a class on FORTH, I remember I brought my handheld computer. At that time, I think it's an Osborne. It's about that big, okay? But it's portable. And I brought that and take a Greyhound from Portland, Oregon to Arcata in Northern California. And that really gave me into the FORTH. And I see, oh boy, this is a wonderful language. I'm not a computer science background, but at least I can understand, I can write something that, to check out my way of thinking. So that's how I get into it. Now, let me get back to the Chinese character, the Chinese language, and maybe a little bit of Chinese culture. So when a lot of people say that, what is a character? A character means in the alphabetical language is quite different from the Chinese ideographic language. And actually in Chinese, 文 and 字, they are two different things. 文 are the simple decomposable pictogram, like the one on the right-hand side, sun, moon, water, that kind of thing. And 字 are the combination of those 文. Okay. Now, another big differences on the alphabetical languages, like in English, 26
Timothy, one moment. I can't see your screen, only you talking, but your screen is not advancing. Your presentation.
I can see you, Timothy. Timothy, the slides are not going on.
Exactly.
You are live video. You are live video, but the slides are still the first slide.
I'm sharing the screen.
But the slides are not going, Timothy.
I can see his screen just fine.
But it's fixed, Cecil.
Okay. On the right hand.
Just try turning off the sharing and then turn it back on again. Sometimes the sharing freezes. And so if you just turn it off and then turn it back on, it should usually, it will probably track you better. Yeah, that's okay. Actually.
Okay.
I can now see your PowerPoint program. That's fine. I guess.
Now working
So
for me.
working.
It was frozen.
Yeah. Okay.
Okay. You see here on the upper left, here is the oldest record of Chinese character engraved on the turtle shell or oxbow. Okay. Now, since that time, this is about 4,000 years ago, 3,000, 4,000 years ago. Since then, the number of Chinese characters increased. This chart on the lower left side is how many characters has increased. Till the 1989, there was 75,684 characters. Okay, and according to my calculation, almost every 3 days, there is a new Chinese characters comes out. Okay.
Holy cow. How do you hold up?
So for the alphabetical language, the alphabets are a closed number set, but for the Chinese, it's an open set. We don't know, and nobody actually can control the number of new characters. Okay, the government can say, encourage you not to create new Chinese characters, but the new concept comes out. Somehow people start use a new character. There's nothing that the government can do. Okay, so let's go the next one. And let's look at this. A Chinese character are composed of what I call the root, and each root is composed of the stroke, which equivalent to the English word and alphabet are made from the stroke. Okay, this is my thought of my understanding of the Chinese character. So all the 75,000 Chinese characters can actually be defined by a set of the basic stroke, which, according to one study, 32 of it. Okay, 32 basic strokes. Okay, now for the alphabetical language, you have the ASCII code, you have whatever the Unicode, that kind of thing. But for the Chinese, in order to operate the Chinese input or information interchange, we need something what we call the input code, so that you can get the right character you want to use. And of course, for file interchange, exchange, you need the interchange code. Another concept is that the font and the glyph in the alphabetical languages are somehow similar, but somehow different. Okay. So one way that when I try to build my Chinese system, what I did is that I took a approach, what I call it, go fresh from bone. In other words, once the basic fundamental stroke are defined, then I can do an outline of that stroke, which to make a different font or different glyphs. Okay. Then there is also a need for a user to type in something to address a given character. So need the input code. And fortunately or unfortunately, I got an American patent on an input method. The definition of my input code is phonetic plus a two diagonal structured code. So, and actually this is a very, on the bottom, around the center bottom of the screen, this is a very interesting thing is that this is a definition of a Chinese character in fourth style in my Chinese system. Okay. Next. Now, when I was looking for a suitable computer language to build my system, one thing I find out quite interesting is that the Chinese character construction and the force are very similar. For example, when we do a square, tube and multiply and semicolon, okay? And cube we can use the square on the top as well, cube, square, multiply. And on here, you see the Chinese character. Ming can be defined by radical root and radical moon and put them parallel together. Meng, another new character which uses existing Ming and then added another radical Ming on the bottom. And for the Meng, another new character, we put the radical, the grass radical, and then Ming. Okay, so that's how a Chinese character can be built with the already existing word in fourth term, a word, okay? And another question for me is why the Chinese kid had to learn English to write program. This is a very serious question. Okay, so at that time when I was doing this, I have Mike Perry, who was working with Henry Lexon to develop FORTH-83, F83. And, you know, I hired Mike Perry to do the work, force development for me. And then we come up with a good solution of what I call a double-headed forth, which was published in Dr. Dobbs' journal. And basically the structure is one, the English header have a pointer point to the code field of the actual definition, but also we can edit a Chinese header, okay, to point to that. So by that, you can have a bilingual or even trilingual language force that, you know, remove the language barrier for the native kids to learn computer language. And my Chinese force will use Chinese phonetic purple morpho because at that time I didn't have a chance to build a Chinese character yet. Okay, so back to the basic question is that if the Chinese kids can write program in Chinese in their own native language. Okay, so with that, we built a Chinese kernel, okay? And we use the forth flavor to do the Chinese character definitions. For example, here at the lower right, this is a definition, the stroke, I mean the root, a given root definition. Then once that is defined, we can go to the top and to define a Chinese character with these roots, okay? And here are the operators, and here are the interchange code. And this line, this column is my DAI code to input a to look for a character inside my system. Now, with this architecture, each Chinese character will only take up 16 bytes. Okay. Now, at that time, I didn't have the time because I started a company and then finally run out of money. I think a lot of people don't understand that this kind of have this kind of experience. And so actually it's not fully finished. But anyhow, I was able to do a Chinese word processor. And this is the letter that in 1984, February 22nd, I used my system to write my mom a letter, okay? The character go from the first paragraph, go from left to right, left to right, left to right, okay? But also the middle section can go from top to bottom. Okay, and the last part is from right to left, just like Arabic language. Okay, and it was done in FORTH quite easily. So can we kind of unite all the computer language? I don't think so. It's Tower of Babel, right? The C guys will hate us, and the Pascal guy will say, you guys are crazy. Okay, we don't care. Okay, but one thing is that language and writing difference cause philosophical thinking and cultural differences. For example, in Chinese, we usually don't care that much about the tense, the gender, the numbers, that kind of thing. 1 book, 2 books, 3 books, 4 books, no S. Okay, that's, and then, you know, before quickly I am going to finish this. The one thing is that I think this is a very interesting idea is, what is a big one? By the way, that's my name in Chinese. And what is a little one? The big one is something that nothing can be bigger than that. That's called big one. The smaller one is something that nothing can be smaller than that. And in mathematical terms, that's, you know, plus infinitive and minus infinitive, okay? But this kind of concept come up in Chinese history about at least 2,000 years ago. So what I'm asking is that, can we start it from software and to hardware, from the Chinese character, Chinese culture, as a starting point, rather than based on the American or alphabetical language. So my wish, I hope somebody can carry on to popularize the Chinese force. The Chinese kid can use their own mother tongue to write program. Okay. Yeah. Also, you know, as now, I think, you know, we've been discussed the multi-kernel FORTH CPU, which is
Designing my own computer.
available, not popular, but available. Okay, and my personal need recently is that I do a lot of homography processing, and the image file could be 100 gigabytes. Okay, so I need something really powerful to do those image processing. Okay, so that's it. And I think I use more than allows for me. But here is my FORTH computer, Novix chip. Thank you.
Okay. Excellent,
Thank you.
Timothy. Thank you. Now is the turn of Philip. Are you there?
I'm here.
We need Timothy, please stop sharing your screen if possible.
What?
Stop sharing the screen, if you can.
Let me bring back the screen. Somehow I couldn't see the screen.
Abraham, you can also stop sharing the screen of Timothy. Timothy, below on the bottom of your screen, where the share button.
Yeah, I just click the green button.
The green.
The green button in the middle. At the bottom.
Of Zoom.
Okay. I don't see. Somehow I lost the screen. I hear you guys, but
You need to
Press the green button. Okay,
Mm.
Timothy.
I think he's lost
Stop
the
sharing.
Zoom.
Stop
hey,
sharing.
I'm hearing.
I think
see,
you first need to find your Zoom client again.
Yeah, that's right. So find the Zoom program. Yeah.
Oh. No.
It's the blue icon far to the right, down in the dock.
You have to go down to the bottom of the screen and then the bar shows up. Move your cursor to the bottom of the screen.
Or to the top, there's
On my screens, it shows up at the top, not at the bottom.
Yeah, you're right. The green on the top there.
The new share.
yeah, just press it and stop the sharing. Okay. Yeah, press the green button. Yeah, you are at it.
You're looking in the web browser at the moment.
I'm not sure it'll work, but you could try an Alt-S.
Oh, some things.
Oh, somehow. Anyhow, sorry for that.
The screen back to us. Okay.
Okay. Okay.
now.
As
Philip
long as
can.
you guys have a control of the screen, that should be fine to me.
I'm told I still cannot share the screen while the other participant is sharing.
Yeah, you're still.
Exact.
So who is
find
moderator and
this-
can stop the sharing?
The moderator is not here, Ulrich. I am trying to contact him, but he's not with us.
Ah, yeah, I see, I see. And as a
Yeah.
co-chair, you can't do that?
No.
Guys,
Drop out of it.
how about Dr. Ting gets completely out of Zoom and logs back in, because that will break his screen
Dr. Huang, yeah.
sharing, and it
Huang.
shouldn't take long.
But
Okay,
not Ting.
Yeah, that's it. Click
Timothy.
that. Click that.
Let me log out.
It's not a problem of Ting. It's Timothy.
Yeah.
Okay,
I
here we
think
go.
that was it. I'm unblocked
Yeah.
over
Okay.
here.
Philip, go
Yeah.
on, please. Sorry for the inconvenience.
No problem. You can see my CC64 small c.
Yes.
Excellent. Good.
Yeah,
So,
nice and sharp.
I'm talking about an old student time project of mine, mostly, which I presented a month or two ago at the Euroforth, and Peter asked me to talk about this in this round again. So here I am. A small C compiler on the Commodore 64. Now, why would one write a C compiler on the C64 in 1989? The biggest reason was that I thought I could. Probably a key reason for a lot of computer software to be made. The inspirations I had was a similar small C compiler by Ron Kane and James Hendricks, published in a Dr. Dobbs book, in the case that I got it. And of course, the Dragon book, the iconic compiler maker's manual. The reason I wrote it in Forth is that this was pretty much the best, most powerful IDE and programming language for any practical purpose that I could find on the Commodore 64. One of the biggest advantages there, especially on the small machine, was the compact code. Well, I'm sure pretty much everybody around here sort of has been there at some point. So this is what a classical C compiler looks like, from which I had to strike quite a lot to limit the scope or get the scope manageable for me. So typically you have a source, it goes to a preprocessor, which replaces stuff. then goes into the scanner, which produces tokens. The parser will produce a syntax tree. Code generator will produce assembly. It might go through an optimizer, then into assembler, which produces object code, and then the linker eventually produces an executable. So this is what I made out of it. I scratched the preprocessor, mostly. Scanner, tokens, parser are there. Abstract syntax tree as such, not really. Code generator skips all the optimizer and assembler steps. Well, the fourth assembler somehow is involved, but we get to this. But essentially, this produces almost runnable binary code, which then at the end gets put together by I would call it a mini linker, linked with a runtime module to either produce an executable or a new runtime module. The properties of the language. So what is the small in the C of the compiler? First of all, it's still kerning enriching. It's int and char as basic data types only one level of pointer, so no pointers of pointers. No unsigns, no long, no floats, etc. So really just int and char, and also no goto, at least so far. The shortcut I took with a preprocessor is that I implemented define as compiler constants. There was a convenient gap in the semantics of C back then, which kind of asked for that. File include is, of course, well, not of course, but file include is still there. There's no symbolic linker. The sort of overall model that I had in mind for this thing was pretty much Turbo Pascal 3. So you have a very, or hopefully reasonably quick compiler, which in one pass essentially produces your binary, your com file in Turbo Pascal's case. So no extensive library concept yet. The parser is handwritten. It's a top-down recursive descent parser, like the default thing that you produce when you go about handwriting a parser. The parser nodes call the corresponding code generator nodes one-to-one. So that is why there is no explicit materialized syntax tree. It pretty much gets eaten up the minute it gets constructed. The code gen is based on a 6502-ish, I want to call it, 16-bit single register stack virtual machine. And the implementation of that VM is via code templates, so binary code templates, and to produce those, the 6502 fourth assembler is utilized. Here's an example what the recursive descent in the parser looks like. So this is the code for parsing the logic OR and logic AND operator. First thing that the logic OR does is it descends to the higher priority logic AND, which then does the same, goes to the next priority bit OR. And after the next higher level is handled, each level looks, is my operator coming? If yes, I'll call something on the code generator, call my next higher node again, and so on. Nice thing is that, at least in this part of the parser where you're dealing with binary operands, and logic AND and OR are a little bit special in C because they stop evaluating as soon as the result is clear from the first operand. But all others, the handling is pretty much the same. The only difference for each operator level is you need to know what's the operator you're looking for, what's your next higher priority, operator precedence, partner, and what is your code generator correspondent. And this lends itself, of course, very, very nicely to a defining word in Forth. So this is actual code from the parser, only I reversed the order in the real Forth. Of course, the higher precedence later called, called by lower precedence operands come first. So I reversed the order here. This is what the code templates look like. So the concept of the machine is I've got one accumulator-like register, which is living in the 6502 A and X registers. I implemented a soft stack for the local variables through 0-page, 1 or 2 0-page pointers. And then you have these little defining words with which you produce something that almost looks like assembler. The only thing in between are these special parameters. Utilizes a special tweak in the 6502 opcode matrix, where there's pretty much one column free that you can use for your own replacement bytes. These are, at the moment of actual instantiating these templates, are then filled with, for example, an absolute address parameter for this sequence, or with a given 0-page pointer, or with a lower and higher byte of an address or something like that. And then the actual code looks, for example, like this. Oops, I can't mark a line here. That you have an immediate load accumulator, which is made up of low-level LDA, LDX, etc., etc. And especially for things like division and multiplication, these code templates, like here at the top, will compile or fill into the binary code a jump subroutine to a runtime module routine. But with this, in this way, I didn't have at that time an assembler or a linker or something available, and I still could get to executable binary code in a relatively straightforward and manageable manner. It's all done almost in a single pass. These code templates, even while the parser is parsing and calling down through code generator to this, I call it virtual assembler, already filled in absolute addresses where they are relevant, for example, for static variables. One trick is that the entire code, binary code for one function, C function, must fit into RAM, so that control structure patches, jump patches forward and backward can be done in this single pass. The second pass is then what I call the mini linker, which really just takes the existing runtime module, attaches the generated code, patches, that's the only thing I can't do in the first pass, potentially forward declared functions, patches those jumps into the binary code, and then attaches initialization data for the static variables. Rule is then, if the end product that you compile doesn't have a main function, then the mini linker will write out a new runtime module. So that is kind of the shortcut for the missing library or symbolic linking mechanism. So if you want to build your next programs based on let's say a C64 kernel library, or if you want to build which is something that I should do at some point, an actual more or less compatible C standard library, this would be a way to produce this. So the new library would then become the runtime module that you use for the next programs that you write. Yeah, and all that together is 18K of indirect threaded code plus the 14K kernel of FORTH giving 32K of size of the binary altogether. Further ideas. At the moment, it's running on the C64 and the Commodore 16. I'm in the process of porting it to the Commander X16 new, Commodore-inspired 8-bit home computer by the 8-bit guy. Don't know if someone knows the YouTube channel. Porting it to Linux as a host is something that I would like to do, just to make it development easier. Then as a subsequent, I've got pretty decent end-to-end tests already, but unit and component tests would be nice. Definitely get beyond the Koenig and Ritchie calling syntax and enable ANSI style functions. I would like to profile some of this. I'm not quite convinced that the compile has to be as slow as it is. One further idea is maybe at some point to output assembler source. The layered design of the thing is actually made so that that should be reasonably feasible. Maybe even to the point that one could use a symbolic linker. And of course, a C library. That's one of the biggest gaps at the moment, to actually port existing, if small, C programs to one of the target platforms. And I think that's what I have. Thank you very much. Happy to take any questions, of course.
I have a question or a comment. This is really fascinating. You know what would be a great tool if you took this little engine that you created that parses C and outputs a language, compiles it. If you could take your same engine and output forth code, that would be a very useful tool.
So basically what you're saying is build a code generator. Yeah, I get what you're saying. Well,
that would be very useful for the Forth community. We could take C source code that's already written for something and put it through your engine, and then have actual Forth code. So you've done half the problem already.
Yeah, targeting Forth as a virtual machine instead of instead of 6502. Forth becomes the machine code in that case.
Yeah, that's a cool idea.
Yeah, when you look at the recursive descent, my mind escapes me. The recursive parser, yeah, its output is reverse Polish notation code, which then eventually gets translated into assembler, or at that point it can be spit out as Forth.
Mm-hmm. Yeah, it could probably be as simple as you would want to build a set of Forth words to. So I'm sure there are some operations that the code generator wants to do that your standard Forth doesn't immediately provide you. So things like accessing a local variable on a classic C stack or something like that. But yeah, fun idea.
I imagine the challenge would be there's a big gap between outputting some kind of Forth code that would work versus Forth code that would be sort of readable and understandable, and rather than sort of a low level sort of regurgitation of what the VM was doing.
Very, very true.
Yeah, that's really good. And so can you run it on a Commodore 64? Is the whole thing actually working? Like you've got 32K of compiler.
Yeah.
And
This is completely self-hosted.
That's pretty awesome.
Or local. So I actually developed 95% of it on a Commodore 64 with 3 170K disks, 2 for the compiler, 1 for an editor, for a small editor.
Wow.
Lots of 12 screens per page printouts to again and again get an overview. So the current development environment actually is that's actually something I'm to a moderate level proud of. Vice emulator inside a make environment, something, including tests. Run the compiler with C test, producing an output, and then running that output again through the emulator and compare the output of that to the Goldens. So I caught a few nasty division and switch statement bugs with that.
Fantastic. Excellent.
Yeah, then I would say thank you very much.
Yeah, thank you. Okay, yeah, some claps and thanks for that. Peter, maybe you can take the mic. Yeah.
Philip, outstanding. Talk you later. I have a contract for you for $1 million, but no problem. John, you are in Sydney, and probably you are the first one to go to bed. Do you want to say something to the group?
Sorry, you talking to me? Sorry.
You want to say something to the group before you go to bed because you are late in Sydney.
Yes, indeed, in Melbourne, in fact. But yes, it's the same time. Yes, I'm going to head off now because it's nearly 2 o'clock. But some great talks. I'll watch the rest on video later. Have a good rest of the time, everybody. Bye.
I really enjoy that we have such an international group. This is fantastic.
John, Merry Christmas for you and your family and all your friends in Australia.
Thank you, and same to you. And have a great summer Christmas in Brazil, because we do it. That's the way we do it down here too.
Oh, thanks.
All right. See you later. And Merry Christmas, everybody. And have a nice white Christmas, everyone else. Thank you. Bye.
Bye.
Well, Ulrich, who is next? Are you in charge?
Yeah, that's Jan Hieronymus presenting his fourth block. That's the next speaker, I guess.
I've tried to share my screen.
Perfect.
Do I have audio?
Yes, perfect.
We can hear and we can see your slides.
Okay, that's good. I write sometimes things on my blog, and also about Fort and how I started with Fort. It's not really a Fort blog, but Peter asked me if I can tell something about it. These are the topics that I want to tell about. Where I live. Peter also asked the last time, where do you live? My first computer and Fort, using Fort. That's my first post that I made about Fort. And then I want to tell something about Create DOS. That's something, I'm explaining that because I also hope there are a lot of beginners that do not use it yet or do not really know how to use it. And then more about defining words to control hardware in Fort. And I want to encourage playing with Fort. Where I live, this is a picture of the environment where I live. I first thought putting a photo, but then I decided to put a video. A small, I hope you can see this. this is an incredible engine, and without that, I couldn't live where I live. It pumps up water. There are actually 2 levels, 5 meter and 6 meter high it can pump. It's one of the most biggest engines in the world. I only show a very short video of it. Because where I live is below the bottom of the sea, all the land you see here was formerly water, that yellow part, and that's where I live now. This is in the Netherlands. I live now in one of the lowest parts in Almere, but I actually came from one of the highest parts, 322 meters in the south of Holland, and that was kind of different, and also different things that, because we live in an exciting time now. When I first started with computers, I could never believe that things would be like now, and hearing and talking to people. That's the 300 meters is not actually the highest point in the Netherlands. There's a higher point, but that is one of the colonies in the Netherlands. And this is my blog post if you want to read it. And I started FORTH using an 11.2 computer. It has an 1802 processor. This is the short diagram of how the processor works. It has 16 registers, and those registers can be assigned to be the program counter or stack pointer or all that kind of things, and that's all controlled by registers. And that when I started, there was not much software available. So I was happy to receive a magazine with things written in it, short assembler routines. The memory was also very small, but there was also a graphic output. And there was also a FORTH version came out for the 1802 CPU. Only the problem is I built a small computer and I didn't have a real terminal connected to it. The computer had a memory that could be shown with a graphical chip, but not the really displaying, not an RS-232 terminal. I didn't have money for that, but there was a program that could create characters on it and acted as a terminal to actually have letters. So I did think I know the assembly code of that terminal program, and due to the good resources about FORTH and the wonderful book of Dr. Ting, who explained everything, how the fig FORTH was working, I did think I could make this working to have graphical output and really use FORTH, because there was not much software available. This is also the processor, the 16 general purposes registers. They are almost the same, but there was a little problem. They were almost the same. They were not actually really the same, because this is how the graphics were made in memory. This is the graphic chip, and there was made an interrupt, and then this chip provided the video by displaying white or black on the screen, and you need to have an interrupt routine who did things like repeating the same line over and over again to make use of the video and to make higher characters. And the 16 registers that were inside, this is a list of the software that was available, the 16 registers that were available. in FORTH, in the FORTH implementation, they were already assigned to things, but also the video graphic routine used those routines. So one of the registers, register 2, is the return stack pointer in FORTH, but it also was used extensively in the graphic routine. So I need to manually change all the code, and in that time I could not use a computer to do that. I had to do is all hexadecimal, write things out, print things out, and also change other registers that contained constants that were used. And after a lot of rewriting, I was able to match the FORTH system with that graphical system. So I had a really working FORTH computer. And that was also a very big step in improving what I could do with the system, because in FORTH I could use an assembler that was written for the 1802 processor and write other programs, and also do little experiments by trying to control hardware and other kind of things. One of the nicest thing in FORTH, what I like much, is the build DOS, or what later became a create DOS function. And I hope there are also a lot of beginners who perhaps don't really know how that works. So I will explain it a very little bit as an introduction. When you use it in a colon definition, you can create a word CCC and then builds, and then every time the word CCC is executed, builds defines a new word, that's in that part is defined how the things are really stored in the memory, and the DOS part contains the code when the words that you have defined with CCC, it gets a link to the part of the builds, and there is included what you can do with it. This is the definition how it's in the FORTH manual. And as a little example, when you normally define a word, you say colon, my first word, dec2 plus dots, point comma, and then you have something defined. Let's say we make, you want to make something like a variable. You can say 15 variable, my first variable, and variable defines the word, my first variable, and it contains the value 15. To make your own defining variable, for example, to create a variable, I create gvar. You say colon gvar create, comma, does, and then close the command. And then when you say 12 gvar, my second variable, gvar is executed. The create part picks up the second var, puts that in the dictionary. The comma takes the first number from the stack, puts it in memory, and that is the defining part. And when you execute it, you get a pointer to that value 12. Another example, when you create a constant, my first constant, say you want to make something act like a constant, you can say my first constant is that variable and fetch that value. But that's a very strange way of creating a constant. You can make it more real. by saying G constant create, comma, does, and in the does part, you put the fetch part that picks up the value, what you first stored in your dictionary. That only works for constant because you don't have the pointer to the memory, so you can't change it anymore. So that's a constant. And so the does part uses the addresses and fetches here the value. I think that this was a little bit boring for all the FORTH people who already know it, but you can use this concept to create your own defining words. And that is one of the greatest things I think there is in FORTH. For example, create a double-sized variable. You can say something like that also have initialized values, for example, 0. You can say gvar create 0, 0, and then does. And that way you can create new things. But there are also other things possible. You can also, before the create part, you can also put words. And you can use that, for example, to create some hardware. These are very old examples. And say you have some bits to control some device. And then a light in the children's room, a light in the living room, another light B, and a light in the bedroom. And say you want to create something to control that hardware, you can say, it would be nice if I could say something like 1, that is 1 is the first bit is high, is for defining the light in the children's room. 2, and that's just the second, or in binary, you can say, a second bit for controlling the light in the living room, and so on. You can do that by making something like a defining word light, creates, and then store that value, and then in the does part, something to control that hardware. So this is a way you can control, you can use FORTH to create things to control your hardware. Perhaps you also want to think, how would I want to talk to FORTH? And then you could say something like off light living. That means I want to turn off the light in the living room, or on light bedroom to turn on the light in the bedroom, or whatever you want. So then when you know that, you're going to think, how do you need to implement the does part? When the does part, when the light living is executed, you can think, let's the on, off, or toggle, or test, or whatever word, put a constant on the stack. So the first thing after the does part, what you need to do is to swap that values. Then you know what you want to do. You want to turn it on, off, toggle, or test. That's then on the top of the stack. And then you can use some kind of case statement to say what you want to do with that light to determine the action. Test in this case is to check if the light is on, or toggle if switch it on when it's off, or vice versa. So it's very powerful to think, how do I want to give a command to my FORTH system, and then you can use the code to implement that. So you can think, what kind of syntax do you want to control that? If you have multiple lights that you want to turn off, you can say you need to, as the word that is executed, the light living or light children's room, eats the first value of the stack. When you want to turn off 4 devices, you need to say off, 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 and then that kind of things, or you need to say off light living, And then you can think, perhaps that's complicated and I don't want that. I only want to say off and then the devices where I want to control. After, when you know that, you can think, how could I implement that? There are different ways to do that. You can create somewhere a variable that contains that first on-off toggle or test, and use that in the thus part to know what you're going to do, and then you can reuse it in different words. Or you can say, I don't eat the value from the top of the stack, so then the action stays there, and you only say off. You can say off, and then the devices that you want to control. Another thing you can think is, I want to tell it quite a different way. Perhaps I want to make one word that does everything. I want to say a word, and I did put underscores between it, saying light living off, or light living on, or light living toggle, or test. You can do that by creating a word colon light that does multiple things. You can say, for example, I want to create one word and put multiple create does things in that big word. You can say, I make first a word light off, was create does part to turn it off, and so on. And then you can say, I make one big word that does that all in one time. By defining it, I need how to do that. Another thing that you can use, you can say, perhaps I only want to say bit 2 does that control. You can also create a special case of create. You can study your FORTH implementation, how FORTH, how the word create works in FORTH, and then you will see that the input from create comes from the terminal buffer or a pad or so somewhere else, and you can store the location before creating it where it's pointing, and then you can make a new create that first stores the location, then it goes on creating that word, putting in the dictionary, etc. And after you put it in the dictionary, you add the part underscore off.
John, excuse me, a short interruption. Please, if you can shorten, because we are with very short on time.
I will shorten as fast as possible. You can change the defining word by removing, by adding something in the create part, and move that things back, do that things again and again. After that, for that you need to study your FORTH. You can do other, perhaps you want to define other ways of controls that you can also add later on in your system. And I want to encourage you to all play with FORTH and use it and think, how do you want to talk to FORTH, and how can you use create does or other ways to make the syntax act the way you like. Thank you.
Excellent. Thank you very much.
I need to find my Zoom screen.
Ulrich, everything okay? You need to, Jan, sorry, you need to unshare your screen.
Yes, I know.
Maybe there are still some questions to John's talk. So, oh, he's gone. Looks like that. So we probably postpone any questions to him until he returns. And if it's okay, I will start.
Ulrich, please go ahead with your presentation. And when Jan comes back, we chat at the Fourth Cafe.
Mm-hmm.
Thank you.
Okay, so let's see. Here we are.
I just left, so I missed a little bit of the questions. You can contact me.
Yeah, we just said we will do any questions and answers to your talk in the Fourth Cafe later on.
Okay.
Okay. So yeah, I will try to have some flash talk where we just look at some aspects, and I will try to stay in the 10-minute limit. I would like to talk about literate programming and what this has to do with FORTH. In the course, we of course learn what literate programming is all about. Also, we need to talk about development directions because this has some influence on literate programming. And I also want to have a short look into what could be an idea for FORTH literate programming, in that you have Markdown documents that have prose text, and you embed FORTH in that and still can produce nice looking documents and programs out of them. So let's see how this works. So literate programming is actually a programming technique that was invented by Donald Knuth in the 1970s, I guess. So there's a famous article that he wrote, and all his tech books are written in that style when he explains the tech program, and also Metafont. He uses this technique. The idea is that you mix prose text that explains how the program works and what it's supposed to do with the actual program, and not copies of the program, but with the actual program. So you have some kind of literate program that has prose text and program text intermixed. And then you have two extraction programs that traditionally have the name weave and tangle. So weave takes a literate program and creates some kind of documentation out of it. And in Knuth's setup, the original programs were written in Pascal, and we've actually created text documents that you can later on process to get very nice typeset documents. And the other program is the Tangle program that looks at the same literate program and extracts all the program text. And in Knuth's style, you can refer to parts of the program by giving the programming parts names, and then you can just use explanatory texts and present the program in any order that you intend to do for didactic and educational purposes, or for understanding. You could just talk about the overall structure and then go into detail and leave things open and explain them later and so on. And so the programs that he had, the weave and the tangle, could deal with this and present the program in any order that you wanted. Right, and this brings us to development directions. So if you think about how you would develop applications, then there are two major directions that you can take. You can start with building blocks that you know that work, and then you collect them and assemble them. So you create your application by combining these building blocks. And at any point in time, you always have something that works. And if you want to have a picture that looks like this, so you have these building blocks and you build nice buildings from them, which are your applications. And if the nice thing about bottom up is that you always have something that already runs, It might not have the full functionality, but at least you can play around with it and bring it into an area that is what you actually want. And in contrast, what you can do, and we heard the top-down term already with the top-down parsers, start with the complete thing, the problem statement in this case, and you decompose the problem statement into subproblems and the subproblems in further subproblems and so on until you reach parts that you say, okay, I can easily implement this. Yeah? And if you want to, then it may look like this. So you have the overall picture, and like in a jigsaw puzzle, you have the different pieces, and all the pieces you can implement very easily, and they might not be shaped regularly as in this picture example, but they could be broader or smaller or whatever. So how do we develop programs in FORTH? So typically we build a domain-specific language bottom up. So we have our stack operators and dictionary words and create does and what have you. And we build up a language that allows us to describe the problem that we want to solve. And we build this from the bottom up. And then we think top down. So we want to solve a Sudoku puzzle, for example, or we want to control a robot arm. So what might be a good language to actually control a robot arm or explain the solution of a Sudoku puzzle? And then we know how the DSL looks like. And then we take this DSL and we build our application bottom up. So we have a language where we can describe the problem in an adequate, appropriate way. And we use the DSL to actually do this. Right. And so that's the FORTH development. And so development in FORTH, it seems to be always bottom up. You don't like to make any forward references where you say, okay, let's decompose this, we explain that later. And so this might be a guideline of what literate FORTH programming might look like. The idea is to embed FORTH programs in Markdown documents. So what is Markdown? That's a very popular, simple markup language for easy text formatting. So you can think of a very lightweight way to describe HTML documents or things like this. And the idea is that the written text is still acceptable to read. And so it's not like XML or HTML where you have these space-consuming begin and end tags and syntax that makes things different to read. But the idea of Markdown is that you really can also read the source document in an appropriate way. And what you can do is you can have headlines and you start a headline by putting a hash sign in front, and you can have bold and italics by using markups, as you can see, double star or underscores to make things bold or italic in the final text. And on the right, you see the rendered text, what it looks like. And then there is something that is called fenced code blocks. In fenced code blocks, there you use the syntax 3 backticks in a row, and then the programming language that you want to use inside the block, and you put program text in there, and you end this fenced code block with a row of 3 backticks. And then the renderer knows, this is program text, and it will style it in a different way, maybe doing syntax highlighting in an appropriate way as you wish. So it knows which programming language to choose by looking at the beginning of the fence block. And so you can intermix program text and prose text that explains everything. So that seems to be a fine way. So you can use the standard tools that process Markdown for formatting, and they produce PDF documents or HTML pages or ebook reader pages or what have you. So you can use the entire Markdown tool chain to create nice looking things, and source code will be formatted in a special way. Of course, you can style this with cascading style sheets and things like this. So it's not necessary that this is colored letters on black background. It could be anything else if you want to. And so what this is actually the weave part that's already there. So process a document like this and create some nice rendered document out of it. And what we need is the tangle part. And the idea is to define a word markdown load, or MD for short, that can extract forth programs that are inside this fenced code block. Yeah, and load this. And so I sat down and implemented this. It actually went ahead and reads the file and parses not just the fenced code blocks, but you can also have inline code. It also deals with that. So, for example, you start Swift forth and make it load the Markdown load file. So at that point in time, you can process Markdown documents like the hello MD that we just saw. And if we go back to the page, you see it defines two words, eggs, which outputs a forth definition, and init, which outputs embed, calls eggs, and then outputs in Markdown. And so if we look at, after we loaded hello MD with MD or Markdown load or Markdown, then it will just extract the forth part of it and loads it into the running system. And then you can invoke init and it would output embed, call eggs, which outputs a forth definition. And then init resumes within Markdown. So you can actually put source code in Markdown files, and you can, with special load functionality, you can load them, ignoring all the prose text and just processing the forth text, which means within the published documents that you give others to look at, it's the actual program that runs in there and not just something that you copied and pasted earlier, but you can really also include tests or whatever to make sure that the published program is actually the right one. Okay, yeah, so that's what I wanted to tell you, especially the way that forth does it is top-down, is bottom-up development. So even here in Markdown documents, you have to first define words and then you can use them afterwards because they are collected in text order and not assembled in some other way. What I would like to hear from you, is that a restriction that you think, well, that's acceptable? Or do you think that presenting forth programs definitions in any order for didactical purposes is really something that you would appreciate? And so rearranging things while loading such a literate program might be worth doing with forth literate programming. So yeah, I'm open for questions. Thank you very much.
Excellent, Ulrich.
That was great. Years ago I did some playing around with literate programming and you know, one of the questions I'd outputted the Moby format, which was quite a hassle. And someone I remember in the audience suggested using Markdown, and it's a great idea to use it, because I think that I never followed up on the suggestion, and that's a great direction to go.
Yeah, so Markdown actually is really the state of the art for simple markup and creating very simple documents. So it's not for, well, you could use it for books, but the formatting that it provides is somewhat limited. But for technical documentation, that's really great, because you can read the original text still and create nice looking documents afterwards.
I have a comment. Our last two presenters were talking about create does and defining your own language. So in my Trying OS robotics language, I tried to make it, you know, so people can speak, you know, to the machine, and you know, forward 10 feet stop is actual code. instead of using the stack for parameters, just make some variables so that you could say something like light off or off light, and I use the word now at the end. So now would go back and look at the two variables, and then that way they could intermix them and they don't be the right position on the stack, for example.
Yeah, right. So maybe that's also a very nice topic that we can follow up on later, is how to build these domain-specific languages, really, and what would be good practice to actually do that. So because I have some ideas of how I would do that, and I hear you talking about other ways to do it. And so, yeah, to exchange common practice would be really great.
Ulrich,
okay.
One thing, if I may.
Mm-hmm.
You said that usually in Forth we use bottom-up approach when we write the code, and top-down is used in, let's say, in a design phase, but we never program that way. I think that actually Forth allows us to do even top-down programming by using prototypes. So I can write the top application board, which is empty, and stepwise to fill words that are actually decomposing the problem to smaller things. So I think that in that way, Forth is very flexible in which approach we choose.
Yeah, but my impression is that still most of the time it's done bottom up, maybe only because I'm looking at final programs. And of course, if I'm designing this, I'm normally using something meet in the middle. So I build up some language, and then I have the problem statement at the top, and then decompose that, and then somehow things meet in the middle. Yeah. So
yeah, I agree. That's actually what I do as well, from both sides.
I do as you do.
Yeah. Okay. Great. Are there any additional questions? So that's not the case. So I try to stop sharing, or is this still sharing?
Yes.
Yes, not anymore. And so I'm switching over to the role of the share, because Peter needs to prepare things on his talk. And so our next speaker will be Cecil Bayona. And Cecil, maybe you want to share your screen. He will talk about 68,000 single board computers and 68,000 FOSS. Great topic. So Cecil, if you share your screen, then the stage is yours. Here we go. Here's the screen. And we can't just hear you right now, maybe. No. No, I see your mic is not muted anymore, but we still can't hear you. Yeah, you say something so that we see if it works. No. Yeah, I thought we heard you later, earlier already. So screen sharing on and off works fine, but so I don't know what about your microphone. Do you have any idea of what's not working? Gee.
John, your mic is muted. Okay, unmute it, please.
I don't think so. When I see his his preview, I think I see that his mic is open.
Cecil, do
yes?
you happen to have a microphone that's mutable, so hardware mutable?
Well, he's using the headset.
Okay, let's try it now. Can people see my
Yeah,
screen?
we see your screen and we hear you. That's great.
Okay, good. My name is Cecil Bayona, and I have many interests. Among them is old retro hardware. I'm particularly fond of the Motorola 68000 systems, and I have a board I bought. Actually, I have several I bought, and it's this board called CB030. And CB stands for Cecil Bayona. 030 is because it's 68030 CPU. And here's a picture of the board. It's a pretty nice board that I got a steal on it because the guy who created this board needed encouragement. So I encouraged him all the time to make and finish this board. So he gave me a prototype, and I also paid him in advance to kind of sort of obligate him to make the board. And finally, to my surprise, when the board was in the final round, he gave me a second board. So I have two of them. Now, it's an interesting board. Motorola 68030 running at 24 megahertz. FPGA to take care of all the I/O. You notice there's no TTL logic anywhere. It's all handled by this Altera CPLD. We have a boot code in this serial EEPROM, a serial port, a second serial port. It's hard to see here, but it's one of those old-fashioned 72-pin memory sticks. The particular board I'm using right now has 16 megabytes. The other board has 64 megabytes. This is a serial board, and this is an expansion port. One card in case you need a parallel port or something bizarre, okay? So it's a pretty nice board. I got both boards for 50 bucks. That's a pretty good deal. The web page, I posted it, talks about it, the features on it. It can hold up to 128 megs of RAM. Now, for those not familiar with Forth, 128 megabytes is a humongous amount of memory. Forth itself doesn't need a whole lot of memory. The Forth I'm going to be demonstrating only uses 29 kilobytes of memory. The rest is for your programs. So the board comes with CPM for Windows for 68 processor. It has the one I have has a 256 megabyte flash card. That is the disk for the system. So it's very fast. And let's get to it and take a look at the board. There's a web page on it that tells you all the good stuff on it. I posted the link. Now I use in Windows TerraTerm. If I hit the reset button, she comes up. It's a little monitor. And if I tell it to boot, bingo, you missed it. CPM 1.3 just booted. Drive A with just bare minimum to boot. Drive B with a lot more stuff. Drive C with minimal OS software and some on FORTH80 and the D drive, we have the same thing. And I explain to you in a second. And the E drive is the entire enchilada. CPM68 comes with an assembler, a linker, a librarian, a C compiler. The C compiler is more akin to a small C. It's not a complete C, but it's plenty there to get in trouble. It doesn't have things like structures and whatever. It doesn't matter. So if I go to the C drive and run F83, there it is. FORTH83 standard of 1983, 2.1.0, which is the latest version that was released, and your typical Forth thing. Oops. Oh. Okay. Why is this thing misbehaving? You know, gazillion words. Now, I have two versions of Forth loaded in that machine. And the reason is, if I, you'll see a bunch of words up here in the beginning, define. Hold on, I must be in the wrong place. Where am I? This one is Forth as it comes out of the box. It has approximately 1,000 words. Words to do with integers, double integers, floats, and your typical Forth things. Compiler. It comes with a meta compiler, so you can compile F83 and modify it. For example, F83 468 was originally FORTH83 for 8086, and it got modified, the meta compiler, and bingo, it generates a system for the 68,000, and that's where we are. So right now, I have a couple of little sample programs. For example, a multiplication table. And this is the vanilla version of 468, 68. So it doesn't have it. So how do I work with inputting programs? Well, it has a Forth editor that I really haven't become familiar with, because one, I didn't use CPM for very long. I moved on to CDOS and then to Chromix, which is a Unix base operating system that had every feature you could dream of. And so I used only CPM for a short period of time. And so one of the ways I can, for example, multiply. Here's a program to multiply, to generate a multiplication table. And you saw that on FORTH2020 recently. So I just enter it into a file. And I can go over here. And it says, you want to paste yet? Yeah, I want to paste that. Now I have delays put in because the interface the guy created does not have handshake with the hardware. So I put delays between characters, and I'm on a character turn, so the system has time to process it. So if I say now mult, it knows what mult is, which is multiply a table 12 by 12 and all the values in between. Okay. Now, one of the features of this Forth is that it has a way of saving. If I remember now, the word. It just saved a copy of FORTH83 with a multiplication table built in. So generally when developing software, I do it bottom up like a lot of people do with Forth. Bottom up meaning you work on the little tiny details first. How to talk to an I/O port, how to send something to the screen. You know, the real simple stuff. You get it debugged and working, you save the system with all that loaded in it. And from then on, when you reboot, that stuff that works is already preloaded into the system, and I don't have to re-enter it again, okay? So if I exit and I go to the C drive, this Forth, I did that too. And as you can see, multiplication is already in there, and I haven't done a thing. So it's kind of handy. A lot of Forths have that feature that you can save a system with all the newly loaded definitions. So I have a couple of programs I loaded in there. For example, print E. E to 100 digits. It calculates it on the fly. And if we look at it, where are we? There's the code for E. It's a little complicated. There are some routines to print stuff and whatever. And it's built in. What else do I have built in? This is my own little program that I often used to see how fast a Forth talks to the system and print, because a lot of the applications I like to do are text-based. So printing speed is important to me. So if I go and enter a number and I say test, there we go. Printing the alphabet, including punctuation and everything, upper, lowercase, 100 times. So what else is in there? Civ, the Civ program. You give it a number, how big to go. You tell it to run the Civ. And what it does, it looks for prime numbers from 1 all the way to the number I gave it. And here's a bunch of prime numbers. Now, how do I know it's a prime number? For people who don't know what a prime number is a number that can be derived by multiplying 1 by itself. There's no other combination of numbers that can be multiplied together to generate that number. So for example, 8087 is a prime number, okay? So I have, if I enter 8087 and run a little word that I enter called factors, it says 8087, you can arrive at that by multiplying 8087 times 1. It's a prime number. If I try 8088, that's not a prime number. So what's it going to do? It says you can multiply 8088 by 1 or 4044 by 2 or 2696 by 3 and so on. There's a whole bunch of ways of arriving at that number. It's not a prime number. A prime number can only be arrived at by itself and 1 being multiplied. That's it. Nothing else is passes the test. So it's very straightforward. So if I exit here, well, I don't have to exit. How do I program in Forth? Very simple. Forth lets you, as you've seen, expand the language by adding features. And by the way, this is strictly for beginners, because all you guys who've used Forth for years know all of this. You can define words and then save the system, and then those words are there to help you out. So, for example, if I want to print the alphabet, colon tells Forth to define a word, and it's going to be called alpha. Oops. It helps if you spell. And we're going to do loop going through the alphabet. So from 127 from 32, that's the printable alphabet, do a do loop. Now, what are we going to do inside this do loop? I gets the index of the loop. We're at 32, we're at 33, we're at 34 as it loops around. Emit the character to the screen, close the loop, close the definition. I just did a very simple definition that if I type that word, that code will execute. And there she is, the alphabet. I can look at it. It has a primitive, it's indirect threaded, Forth. And so there's a literal 127, it goes into the stack. A literal 32 goes into the stack. It executes for do. It remembers those two numbers. I gets the index, emit sends the character to the screen, loop loops around back to the do. If we haven't hit the target condition, the target condition is that I reaches 127. And get out of town. Okay. A semicolon is the end of the definition, and the system's happy with what it did. So it's a very nice language for interacting with hardware. I started getting interested in Forth. I was a hardware engineer, and I needed something to be able to test hardware to see that it was working correctly as designed. So with Forth, I could write little programs to test the hardware and tell me whether it's working or not, show me whether it's working or not. So in a company I work with, we made CNC equipment. I would design hardware and do a little programming, and I would do all the diagnostics. I did it all in Forth, and it saved a ton of memory. But here we are. So CPM is an interesting OS. It's extremely primitive. I was looking yesterday through the list of commands. Oops, I'm already out. For example, if I do a directory, do you notice something? There's no subdirectories. It has a sort of kludge called users. So I'm in the C drive. So if I say I'm user 1, okay, 1C, I'm in the C drive. If I do a directory, there's nothing there because I haven't put anything there. That's how you group collections of code and not have a directory that has, 2,000 entries. So it's very primitive that way, but it's kind of handy. This is the status on the system. I have 4 drives that map to that flash card. And there's 4 drives that are 7K, and some of them got stuff in them. 7, not K, but 7 megabytes each. So here we are. I'm not sure about the future because I want to work with this card more and the 68,000. It already has a set of tools for CPM, which makes me happy. By the way, how am I doing on time? I forgot to start my clock.
Cecil,
yeah,
we are out of time. I'm
okay,
the next.
so I'll terminate it there. The future is either use CPM or go bare metal with a Forth, and that has its advantages because Forth is easily modifiable. And the alternative is there's Unix available for the system. And so I don't know yet what I'm going to do, but it's a pretty nice machine and I'm pretty happy with it. And it runs pretty fast. Thank you.
Yeah, thank you very much. Maybe there are some questions. So yeah, thank you very much. I appreciate some guys still using F83. I'm a big fan of F83. Used it for a long time in the 80s. Yeah, right. And I collected different versions of F83 on my GitHub account. So if you're looking for the 68,000 version or the CPM80 version or the MS-DOS version, then you can find them all in the single repository. Are there more questions? So, right. Here we are. So then I would say we proceed our next speaker. I'm very happy to introduce Peter Force himself to talk about how to install Forth on ESP32 and the projects you're doing with that, Peter. I'm excited to learn about that.
Thank you, Ulrich. Hello, friends from the group. Here, Peter from Brazil. You see the Christ from Rio de Janeiro on my back. I don't live in Rio de Janeiro, but not very far, 300 kilometers from Rio. Cecil, you did a great job. Later we talk about your card a little more. So my presentation is about eForce, which means an easy force made by Dr. Ting and presented on the Maker Faire. This force, Dr. Ting will explain later when he did this. It's a very known force in the community, and it was presented on the Maker Faire 2019 with Brad Nelson and Don Golding together. They created a robot group of the SVFIC. You see here the logo of the Silicon Valley Force Group. It's one of the first or the first group in the world from where we all learned everything about force. So what Brad did on top of the eForth is a very clever application. He created a web application installed inside the Arduino IDE of eForth. So in Forth, we use the term keys. This is not the keys from a woman or from a man. This is a keep it simple, stupid. We learned this from Charles Moore, the creator of Forth. And it's very important for this presentation and for everything that you are going to see in Forth. Forth tries to make the things so simple as possible. This Arduino IDE is one of these examples because everybody knows Arduino, everybody has the IDE, and what Dr. Ting did, he created eForth on top of this wonderful, easy to use IDE. We have two versions of this chip. One is the VROOM, and the other the do it. The difference is only in the pinout of the chip here on the pins, so you must be careful when you install to watch which version you have. Why is force important for a maker, or why is force important for an Arduino or hobbyist or professional? The advantage of force over C is that you got an interpreter and, look at this chart here, and compiler. It's not an interpreter and it's not a compiler. Forth is an interpreter and compiler. That is the great thing in force. This allows you to go ahead directly without compile, download, and debug process we all know from C. You simply write and test your code incrementally. And in this opportunity, with this interesting web interface, you can do it over Wi-Fi. So you have no cables, and you can work with the ESP32 over your browser. More advantages from Forth over C. Forth is an expandable language. This is very good for automation and robots because you can create an own language about force. You can, for example, create a G-code interpreter, or you can create a robot language like human language. This is very, very interesting. Something you can't do in C. You can't do in C, and in Forth is much easier to produce. This is what we call a human language. Use your own words to program your CPU. Another advantage of Forth is it is really much more compact. So normally, in my experience, I have 3 to 10 times smaller code in Forth than in C or in similar languages. Well, let's install eForth. What you need an Arduino IDE installed in your computer. And of course, the chips. This is my board here connected over Wi-Fi. This cable is only for power supply. I'm not using any connection. And you see here the interface of ISP32 Forth. Where you get the files? Dr. Ting was kind and set up all his work on public domain a couple of years ago. And you can go to Forth.org. This is the link. I will put everything later on the Facebook page. And you see all the work of Dr. Ting along over the years. It's easy to download all zip files, no trouble. And this is the file we are going to use, ESP32 Forth web browser. So you can click on that file and you will get here a zip. I am doing this right now. And this zip you copy to your sketch in your Arduino. So when you have an Arduino, You know, everything is stored on sketches. Here is my sketchbook. I don't need to copy because I already have it here opened. And this is the file we are using, ESP32force _62. This is where you need to take care. Select the Arduino IDE and your ESP32 model. There are plenty of models, and here you must take care with the pinout, what we talked before. Almost all are the same. There are very few differences, but select the do it or ESP. There is another one. Which are the standards. These are the standard boards. After that, if you got this and your ESP32 connected by this cable to your computer, you simply verify, compile, and upload. It's such easy. So sorry, I forgot one point here. You need to look for your IP. You need to install inside this code. There is a place here. You simply go down the code and try to find where your IP definition is, and put your router and the IP of you have chosen. In my case, it's here working. I choose this IP. So this is a fixed IP. And this has the advantage, you can connect to your Arduino, to your ESP32 over your smartphone. So this is something very simple. Everybody who is a maker or who knows how to deal with an Arduino can do that. But what have I prepared here? Look at my ESP32. When I want to light a LED, I simply press here the button and you see the LED. We got an analog to digital converter, so I prepared here a potentiometer. This pot, I can request here a value and I get a readout of it. You see, I modify and the number changed. Which is this number? This number is on pin 34. So I can access, can you see my screen here? I am typing. You got here a yellow text input. So you write ADC and the dot is print in force. So I am requesting on pin 34 what is there, and it is 2,500. I change the pot and look again. Dot, and it changed the number. What else have we here? I got here a motor. I got here a servo motor. I want to show you what I do normally with force. I do CNC applications. So I wrote a couple of words. You see here, this is my program, a little program, only to show you how to move a servo motor. It's very fast and easy. So I want to make 1 RPM. So I make 1 RPM here. Look the motor. I want to go in the other direction. So I do -1 RPM. I look at the motor. Now I do slow. This is slow, sorry. I do fast. And I do 1 RPM. Now look. -1 RPM. And if you take attention, I got 2 LEDs here, one green and one red. And when the motor moves, it's spinning and the LEDs change. You see, these are the steps I am sending to the servo motor. If I do -1, both LEDs are lighting. This means one is the step and the other is the direction, and both are changing according to my commands. Here you see the words I have inside this, and these are the words I created to move the motor. I created RPM, I created fast, I created slow, I created clear screen, Peter, some test. MMT is a move motor. Move motor is MMT is an abbreviation, millimeters for moving a millimeter, etc., etc. We will do other. We are short on time now, so we will do in future more about this. Interesting option from Dr. Ting and Brad and Don, but probably you have some questions you want to ask me, so I am finished here.
Yeah, thank you very much.
I have a question. Do you hear me?
Yes, go ahead.
Okay. Can you show us the steps that you do if you include a file? For example, hello world.
Hello world. Perfect. I do a column. I write, for example, Peter.
Sorry. Not interactive, but if you have it on in a file on disk.
Oh, excellent. I do. So I go here to choose a file. This is in Portuguese because when I compiled, the Arduino IDE choose Portuguese, but you will get it in your language, probably in English. I choose a file from here, and I take here my Peter. This is my file now. So I open, and you see it's uploading into the Arduino.
Okay.
It's extremely easy. This is extremely interesting. Please, everybody, buy an ESP32 urgently and follow this incredible PDF from Dr. Ting. This is a wonderful project. For your kids, for you, for your neighbor, for everybody. Is everything explained? This group is fantastic because we got all the 3 guys in the group, Dr. Ting, Brad Nelson, and Don Golding, and you got me also. Now I came in the last minute, but we will help everybody to force. You need to force, guys. Go ahead, buy an Arduino and install this. This is all. Next participant.
Okay, thank you very much, Peter. This was really an excellent talk. I really appreciate also the setup in showing an additional camera view of your things, and maybe you can share what you did operating with 2 cameras at the same time at some point in time.
Excellent.
Yeah, that's really great. I could really make use of this kind of setup in the lectures I give. So that's rather nice.
Thank you, Ulrich, so much.
Okay, right. So thanks again. Our next speaker is Bill Rexdale, and we already heard about builds does. And as I learned, Bill Rexdale is also responsible for proposing the initial version of builds does. And so now, Peter, I think you have to unshare your screen, and I would ask Bill to share the screen so that we can look at your slides.
We're coming.
At least we can hear you. That's great. Here we go. Yeah, Bill, please go ahead.
Ready. We're getting ready. Very good. Great to be with you, gentlemen, worldwide. This is, I guess you call a domain-specific language, DSL. It's expanding forth into the form of matrix language. So today what we're going to cover is a quick examination of the usual matrix simulation syntax that you'll see in other systems. A fourth appropriate equivalent, the matrix word set. We'll demonstrate some simple operations on matrices and some matrix calculations. First, the credits. I've been using Win32 Forth from Andrew McEwen and Tom Zimmer. At the very end, you'll see that I've written a 70-page manual on this implementation, and it's posted on GitHub. And you'll see the link at the end. I'd also like to thank the European team who updated Win32 Forth in the early 2000s, going up to about 2010 or 12. They've made it so it's contemporary and works clear up to Windows 10. And finally, Dr. Julian Noble, the late Dr. Julian Noble, he died, I believe, in 2008. He wrote the book Scientific Forth, and the key concepts of the syntax and data structures are from Dr. Noble. First, let's look at how to create a float matrix. All of the number outputs are using a floating point in Win32 Forth. So we create a matrix of 3 by 4, and we use a simple word that's create with a little curly brace, and we name it Forth with a curly brace. Everything with a curly brace on it either generates or absorbs a matrix. So we've created that matrix, and by the way, create is done with a builds does or create does. So now that we have the word first, which is the matrix, we'll then apply the operator to it of list. The little curly brace list accepts the structure of the matrix Forth, list as contents, and here we see that it's a 3 by 4 matrix, and all the values contained in are 0. Here's an example of direct data entry. We want to type in information right from the keyboard, so we write down first with a curly brace, which opens that matrix, and then the little detailed syntax with the brackets, the vertical bar, the closing braces and brackets says accept the following numbers, and we see row, 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 column, column, column. After making that entry, the second line says first with the paren list, and we list the contents, and we see exactly right. The first row is all 1s, the second row is all 2s, the third row is all 3s. So our direct entry is working. Let's automate filling values. This is mostly for testing. We have the operator fill shown in green. So we address our matrix first. We use the curly brace fill to fill it full of integers. And then we use our list operator. And we see now that the matrix has cell values 1 through 12. Again, this is typically used for testing and a quick look. Here's an example of matrix math. We give it the 3 values, the first value, the second value to be entered, and then the third matrix is our destination. In this case, we want to double a matrix. We start with first, we add it to first, and we store it in first. In the green down below this, equivalent in fourth would be taking a variable A, another variable A, add the 2 together, and then stored in A. And we see exactly on the bottom, we now have double the values in each cell, where at the beginning top left, we had a 1, now we have a 2, then we go 4, 6, 8, down to the lower right. It was 12, now it's 24. So we've added the matrix to itself. Note this could be anything from 1 to 3 matrices, which would supply the 2 inputs and the output. Here's a simple transpose. Again, we create the matrix first and we fill it full of numbers 1 through 12. The green list shows that that's how it's currently structured. Then we address the matrix first and then do the little curly brace transpose and list it. And we say now the rows and columns have been transposed. And the first column now is 1, 2, 3, 4, where it used to be the first row. Now here's a traditional matrix syntax, and we'll see how it matches up with what I've done. At the start, we have a C with a 1, 3. So that's our destination. It says take the following information, put it into matrix C, row 1, column 3. The input is taken from matrix A and matrix B. In this case, the input always has a variable name. It designates cells within the matrix and then some operations done on those values. There's the equivalent in this format. In the lower portion, it says and also note that in this matrix fourth, all rows and columns are 0 based. In traditional matrix notation, rows and columns begin with 1. In fourth, they begin with 0. I tried to make a dual system that would allow you to switch between the two, and it got hugely complicated and I gave up on it. So I followed Dr. Noble's lead, which is all matrix rows and columns are 0 based. So at the bottom in the green, we see that we say address matrix A. The double braces lets us address the components within that matrix, and we take row 1, column 1. We convert that to an address and then do the floating point fetch. And for the B matrix, likewise, we address within it. We pick rows and columns 1 and 2. The double brace converts that to an address, and we fetch from that matrix. F plus adds the 2 together. We then address matrix C, in this case, row 0, column 2, and F store, floating point store, stores into it. Note that the terminology is more verbose than the traditional input. However, the parsing and the sequence and the logic is precisely clear. So the traditional syntax being very terse, but not clear in the parsing. I've given a sort of a fictitious example here about how complicated it can get. But here we see we're addressing A and B matrices, extracting components, putting them into C. Parsing is not clear and the order is not clear. So in fourth, we can pick it apart. We see the clarity. In fourth, the A brace gets the address. The double braces gets a descriptor. In that case, the descriptor is address, rows, columns, and bytes per cell. The 2-3 specifies rows and columns. The double brace gets the storage address. And now we have on the 4 stack the address, and then a floating point operator operates on that address. In a double row situation, we see The green is what you see visible with the A brace. The lower address is what's on the 4 stack. The double braces and the gets us to the row and column. The double brace on the right says give us the address. And finally, fetched, the floating point fetch gives us on the floating point stack a particular number. So here's the actual code of that word fill. And this is written in Forth. I'll run briefly through it. First, we have an operator do a set up the loop, and we have a double do loop, rows and columns. At the second do, we see dupe j times I plus single to float. This gets us our stored value that we want to store, computes the stored value. And then with the green arrow, we see the portion that is actually doing the addressing within the matrix. Over a double brace gets us the address of the matrix. We use a J and I address in row and column, and then the double brace fetch stores into that. So we see that it's clear, it's clean, and it's actually quite brief. The double loop goes rows and columns. At the very end, we have some housekeeping where we have to drop some numbers. So there's our address is filling a matrix with the row column values from 1 to n. This is a D chart of that operation. You can see how we set up the loop. We get the columns and rows, over the rows, and then over the columns, we get the cell number. We store it in the next column. We store it, and then we can move to the next column. Column by column until it's exhausted. Then we go to the next row and over rows until the rows are exhausted, and then back to the main loop. We drop the value C and we drop an address. Simple logic, very Forth-like. So some details that I mentioned before. The Forth matrix is 0 base for rows and columns. Words that have the single brace on them are either generating or using a matrix address. This is just a physical address of where the matrix data is located. It's the parameter field of a bills does word. The word with double brace converts that matrix address into its descriptor. This reaches into the create does parameter field and pulls out the address, the rows, number of columns, and bytes per cell. In the floating point matrix Forth, the bytes per cell is always 8. And the words with the double brace, opening or closing, operate on that descriptor, which also depends the fact that the row and column values have been specified. So here's our summary of the words that are available. We can create a matrix, a couple of flavors of that. That's again a bills does word. We have support words, which will list and fill a matrix. These are developed very early, so we can see what the results of our partial work is. The data entry came along second, which allowed me to put in values directly into the matrix. And then manipulation, the classic ones of transpose, invert, determinate, I, and so on. All written in Forth, all quite brief and quite clear. Matrix math, we can add, subtract, divide, and multiply matrix, and then the matrix form of a dot multiply. We have row and column operators, so we can exchange rows, exchange columns. The stack address allows us to manipulate the addresses of the matrix itself. In other words, the dupe bracket will actually retrieve and duplicate a matrix and make it ready for further manipulation. And then finally, cell math. Within the matrix, we can address the components. We do a floating point fetch, floating point question mark, floating point store, plus store, and so on. The work's divided into 4 levels. Level 0 are the internals, the words that you really don't see when you're doing much matrix manipulation. These are the internal words like seeing if you have a matrix that's row and column conformal and so on. Level 1 is doing cell to cell manipulation. These are manipulating actual Forth addresses. Level 2 is manipulation of the matrix by row and column. This is expanding and it's currently under development. Level 3 then is matrix level, where we can create matrix, we can fill, we list, we copy, we can transpose, we can do multiply. And if you're doing analytic or research work, most of your work is done at this level. So in summary, I use MATLAB and a clone of Octave, and about once a year, I come back to a live project. And unfortunately, I have to kind of relearn and refigure the semantics and syntax, flipping back to cheat sheets and to books. The manuals explain each single data structure, but they do not give the overall parsing order. So you have to figure it out by experiment or by having gone through it. Therefore, what I need is a reverse Polish syntax that needs no refresher course. When you read the code, you are reading the exact execution order. And of course, matrix fourth is the answer. Here are two references on GitHub. You can find me by name, Bill Ragsdale, and I've posted a matrix fourth word set. It's amazingly simple. It's only about 80 lines. And then finally, here's the GitHub reference for my Win32 fourth guide. As I mentioned, it's about an 80-page book. It is in Word format, and it is continuing. In that document, you will see many cases where I put a few asterisks and say additional work needed here. So do we have any questions?
Wonderful read. Excellent.
Good.
Yes, thank you very much.
Good.
So are there any questions? Yeah.
Good. We're all speechless, standing in awe. Very good. Thank you.
I have one. Sorry, I have one single question. The size of the matrix, is it also included stored in the system?
When you define the matrix, the word create does it, and you specify the size. So if you want a 10 by 10 or 20 by 20, you say 10, 20, create, and the matrix is constructed to that size.
But that values, are they also in the definition that you can pick them up to see later the size of the matrix when you?
Yes, if you address a matrix by name, say the example I had was first, put down the double braces and then type .s, you will see the row and column, the physical address, and the matrix cell size. There'll be four numbers in a row.
Okay,
So
that's returned. Okay,
yeah.
Thank you.
Good.
I also have a question of how do you allocate the memory for the matrices? Are they in the dictionary all the time, or?
At first glance, a matrix looks like a variable, because when you execute the name of a variable, you get its physical address in memory, just as you would for a variable. And located at that physical address are its parameters. Its number of rows, number of columns, cell size, and its address. So one might, so addressing a variable gives you its physical name, its physical address. The double braces give you its descriptive parameters.
I see. And this
very
is
clear, very open, very interactive.
I see. So if you create a matrix, then it's allocated in the dictionary, or do you have some kind of heap that you manage?
Nope. The heap is a big issue. Because in this case, the matrix is compiled in memory and its fixed location, and its dimensions can be altered, but its size cannot. So you can do a transposed in place because the rows and column product doesn't change. In lieu of a heap, what I do is I go to dictionary space above here and set up a transient storage area. So that transient storage area allows me to copy a matrix from the dictionary into the transient area, operate on it, and then copy it back to the dictionary. This allows me to have short-term matrices of arbitrary dimensions without consuming dictionary space. However, that transient space is only good until the dictionary size expands and the location out here changes. So I go about 100 cells above here, create a simple structure that is it has a name named transient, and you know, you can do operations. So when you're doing things like transpose and dot multiply, you need those short-term workspaces. But expanding into a true heap structure is a major change into memory management.
I see. Okay, thank you very much. So, are there additional questions to Bill?
I have a question, if that's okay.
Sure, go ahead.
Bill, during your presentation, you showed a chart. I'm not sure I'm familiar with this chart. What did you say it was called? G chart?
You bring a topic warm to my heart. I will try to keep it very brief. I've done several presentations on D charts. They were developed by Dijkstra in about 1972. It is a streamlined form of flow charting, which lends itself to Forth extremely well. On the Silicon Valley Forth postings on YouTube, I have a talk posted there on D charts.
Okay, I'll make sure to look that up. So D is for Dijkstra.
Yes, that's correct.
Yes,
okay.
The first FORTH2020 talk, Bill did also the D charts with us. It was fantastic. I loved it. Who is next now? Sorry, Dr. King. Where is Dr. King?
He is with us.
Okay, I'm here.
Okay, yeah, you can share your screen, and we're happy to hear what you will tell us about the eForth compiler in C and how the ESP32 force is actually done.
Let's see. Okay, everybody see the projector?
Yeah, yes.
Okay, good.
And we hear you.
All right, so the topic is the ESP32E4 compiled by C. And I just want to go, let me see. Okay, so the summary of the subject is from Harvard to Princeton about the architectures of the computer languages. And I talk about the macro assemblers written in C, which built the ESP32 eForth. So there's start with a primitive assembler and write macros to build a bytecode, to assemble bytecode, and macros to assemble colon words, and then build the structures inside the colon words. And the level 4 is, of course, ESP32 eForth itself. C, as most other languages, assumes a Harvard architecture with separated code and memory spaces, separated code and data memories. But on the other hand, the Forth assumes a Princeton architecture with a unified code and data memory. And with this Harvard architecture, C as a compiler is very limited. C cannot compile variable length bytes and word structures, but Forth must have a dictionary with extensible variable length fields. And with that requirement, C as a vanilla C compiler cannot compile Forth. But C at runtime can produce very complicated data structures, including a Forth system. So we can build in C a Forth kernel of bytecode and a Forth byte assembler and many macros which can assemble Forth words and build the complete Forth dictionary. So ESP32 Forth actually it emulates EP32, which was a 32-bit Forth microprocessor designed according to the architecture laid out by Chuck Moore. And ESP Forth is a universal byte machine, which executes bytecode sequences stored in a memory. So here is the byte engine, one line of code in C. So it just picks up the next byte in this data memory, in this dictionary, and then execute that bytecode from this primitive code table. So the level 1 assembler, if I want to compile a Forth system, the minimum is something that can compile bytes and words. So in the C code, I opened up a big array for dictionary. The C data is a byte array, and the data is the same array, but organized in words. And the pointer P is a byte pointer, and pointer IP is a word pointer. P and IP are always related by a factor of 4. So here is the byte assembler. This is a level 1 assembler. So with this C code, you can add 1 byte to the dictionary. And with this 1 line of code, you can add 1 word to the dictionary. So C data and the data are the same array, but with organized in bytes or in words. But you just have to access them with different pointers. So once you have that level 1 assembler to assemble byte or word, then you can build a much more sophisticated assembler by giving each byte a name and have a macro header, which can assemble a header in the dictionary, and a macro code, which can assemble a sequence of bytecode into the Forth dictionary, and thus build a primitive code, because this engine executes only bytecode. The level 3 assembler, which I call the macro assembler, and you can Forth words are given names, and the macro colon would assemble words into a dictionary to build new Forth words. And for the forward or backward references, you need a label to mark word sequences so that you can refer them later. It's kind of awkward to use label to do the assembly because it requires two passes. You have to do the first pass, locate all the words, and in the second pass, you would be able to have the correct addresses to compile them. So to to get around that, I created more macros, which does the structure. So I have if, which is a macro, and which will assemble the true clause, and else would assemble the false clause, and then would terminate this if, else, then structure. And so it's for next for loops, and then begin until again while repeat for indefinite loops. And these macros allow me to assemble structures in fourth words. So this way, I can build the entire fourth system inside C using a C compiler. So ESP32E4.ino is a single file of C code, which is compiled by Arduino to generate a working fourth system on an ESP32 kit. And it allows me to access all the ESP.io devices and all its facilities, all the C callable routines, including Wi-Fi, which we hope to use to control the AI robot. Okay, in conclusion, C is a universal assembly language, according to Will Baden. C cannot compile complicated structures, but in runtime, C can generate very complicated systems, even like ESP E4. Hence, we bridge from the Harvard architecture to the Princeton architecture. Thank you very much. Any questions?
Wonderful, Dr. Ting.
Let me try to.
That was great,
Dr. Ting,
Dr.
this is
Ting.
Greg. Can I ask a dumb question, please, sir? When you talk about the Princeton and the Harvard architecture, how would you describe the two differences between the two?
Let me just cut off my screen, if I may. You are still sharing? Okay, stop sharing. Okay. Okay. All right. The Harvard architecture is all the computers first designed in the 40s. Okay. Having program memory and the computation memory or I/O memory implemented in different manners. Okay. And in the Harvard architecture designed in Harvard, the memory is still, the program memory is on paper tape. Okay. And so the, let me see, in the, I cannot remember all the code name. In some other machines, the memory is, some computation memory is in vacuum tube, and some memory is on disk on magnetic materials. So they are all organized differently.
Mercury also, Dr. Ting. In Mercury drums, no?
Okay. Yeah, but when the von Neumann visited Pennsylvania State and look at the electronic computer they built there. And he immediately felt the computers should not be designed that way, because program memory and the data memory does not have to be different. They can be the same. And so he went back to Princeton and wrote a report and proposing what he called the von Neumann architecture, in which the memory, the program memory and the data memory are the same, are in the same electronic memory. And so this greatly simplifies the computer architecture, and it was mostly followed by later computer designs. So that's what the Harvard architecture and the Princeton architecture are named.
Thank you, sir.
Excuse me. Okay, I think that this is only a very brief summary of what my thought process in building the FORTH system. Actually, every FORTH system are built basically that way, from the very basic comma and C comma, and you build the entire FORTH system, and it just depends upon how sophisticated you want and how easy you want to control and carry out the building of the very complicated FORTH dictionary.
Thank you, sir.
I have one comment. I'd like to see Brad do a talk of the C extensions that he did to Dr. Ting's eFORTH, C and eFORTH. And there was a question earlier about pulling in other C code and creating words. And I know that it has the capability of doing that. So that would be pretty cool.
In dealing with the ESP32, this kit, this computer is not a, it's a beast. It's very complicated. And the CPU, there's no access to the CPU. So, the only way I can get a handle of it is through the C compiler. But the advantage is that there's a ton of code already being developed with this system. So all you have to do is calling the C routine. So if I have a system programmed in C, I can call all these utilities directly, and that makes the Wi-Fi. I cannot program the Wi-Fi. I don't even know where to start. Okay, but in ESP32, you are given the library, the Wi-Fi library, and you can tailor the command to your need. So this is what I think that's the only way we can use ESP32. You cannot bypass the underlying the compiler or the OS.
I think that's a huge feature, and it would be good if you could expand upon that in future talks.
Ask questions.
Yeah, are there any more questions?
Guys, yes. More questions, Ulrich?
No, I'm happy.
Okay, because we are very short on time, everybody extended.
I have one question, maybe.
Yeah, Thomas?
Yeah, Dr. Ting, very nice talk. And I started FORTH some 30 years ago, but now I switched also to Python. What do you think of quantum computing? Do we have a chance to do FORTH on quantum computing? Because when I was at a CeBIT 2 years ago in Hanover, the central fair, you know, CeBIT, one of the world's greatest fair, there was the IBM quantum computer, and they showed some Python libraries or Python interfaces, so you can program their computer with Python. Do you think this will be possible also with FORTH?
Yeah, you know, in the Silicon FORTH meetings, Silicon Valley FORTH interest group meetings, we have a fellow who's talking about quantum computing many times, but I just couldn't understand anything he's talking. I don't understand the quantum computer at all, and I just don't understand how it can possibly work. Okay, and but you know, all these big companies are behind it, IBM, Google, and everybody. So it must be real.
Yeah,
but I don't understand it.
And of course, you can use FORTH as an interface language to whatever machinery is behind that.
Yes,
I don't see why Python has any advantage. On that
Ulrich, what you're saying is very interesting. We got another German, very clever guy, the Bernd Ullmann. He works with analog computers, and he did a wonderful presentation. I invited him today, but he's probably making an analog something with his. He lives inside the computer. He's very busy every day, and he used FORTH, camel FORTH, in a card to interface to his analog computer.
Yeah, right.
Are
there any additional questions?
Yes.
Yeah, I wanted to ask one. Dr. Ting, what is the difference, or how does eForth differ from ANS Forth? I'm new to Forth, so I don't know.
That's a very serious problem. Okay, I think Don and Don's talking about the running course FORTH tutorials. With starting FORTH. Use starting FORTH as the basis of tutorial, and of course, starting FORTH seems to be the best book on FORTH. But I'm very concerned because the eForth or eForth in general is not compatible with ANSI FORTH. Everything else are pretty much the same except the loops. Okay, the loops, the do loop is the standard FORTH loop, and in eForth we use the for next loop. And I'm hesitating to expand eForth to include do loop because you know, do loop is obsolete. The reason why Chuck Moore wrote the FORTH with do loop was that he's tried to emulate Fortran loops. So if you look at the FORTH loop command structure, it basically does what Fortran do loop do, okay? And I think a number of years ago, Chuck Moore actually apologized that he designed the do loop in the beginning. And his thinking is that the for next is a much more efficient way to
Dr. Ting, I have the sources of the do loop extension for eForth, so I can share with our friends on the Facebook page. I will do that.
Yes, yes, I think please short. Do. Please do. I think I'm just waiting for somebody to volunteer to put
I got it.
To put do loop. Okay. Yeah. But I will not do it.
And the for
I will not do it because this is philosophically against my guts. Okay, because do loop is complicated, and it cannot be mechanized. Okay, so when Chuck designed the P series of processor, he just used the for next, because the for next, the next command can be condensed into a single instruction. And in the EP series of processor, the next is a single instruction, and it executes in a single cycle. Do loop cannot do that. Do loop requires two parameters. With two parameters on the stack, you have to do lots of jugglings on the loop indexes to get the loop to work. So it is very inefficient. And if you look at the next instruction, it is a single. If you design the CPU correctly with the data stack and the return stack all in the CPU, then next can be a single cycle instruction. So you can actually in a single cycle, you can keep the loop going with the minimum overhead. So with that advantage, I'm not going to implement do loop in my eForth. But your eForth, that's yours, okay? And I'll be glad to see that somebody does it. And because if Don's going to run his tutorial based on starting forth, he will need do loop. So.
Okay, thank you very much. We can elaborate on that later on. Thank you very much. A very nice talk, and I appreciate your opinion on do loop and for next. And so we are having our salutations, and Ilya is probably well known to the group, but I didn't know he missed his salutation. So Ilya, are you prepared to talk about yourself for 2 minutes? We can't hear you.
Hello to everyone.
Yeah, now we can.
Yes, yes, I want just to say hello to everyone, and sorry, I don't yet implement something perfect to show. I hope next month I will show something, maybe in hardware, maybe in software. For now, I'm working on Objects Pascal virtual machine for FORTH with multi-threading. But like for Sun CPU or for cross compiler, I want to show my screen and want to show something real. before my notebook camera. So hello to everybody.
Hello, and we're looking forward. We already had your workshops, and so we're looking forward how the story goes on.
Ilya, thank you so much, and Merry Christmas for you and your family. I know you don't have Christmas in Russia. You make in January.
We have a New Year.
Okay.
We have New Year, so we have all night between 1st of December and 1st of January. Nobody is sleeping.
Okay.
Include children's. So
a lot of vodka, vodka or another drink.
No, not yet.
No, okay.
Already not. It's not for vodka. It's not. Many people not drink alcohol at all.
Perfect.
So and at least I can. It's not visible from my window because of next home, but 10 kilometers in the window is Kremlin. So hello from Kremlin to everyone.
All the best.
Okay.
Thank you, Ilya.
Okay,
nice.
I'm waiting for feedback. I'm waiting for questions. I'm waiting for communications. Bye.
Okay, thank you very much. And yeah, next salutation is from Brad Nelson. Brad, are you prepared to talk about yourself for a little while?
Sure. Hi, I'm Brad Nelson.
Brad.
I work on a variety of different things that seem to intersect with Forth a good bit. One commentary actually on the question of eForth and compatibility with starting Forth. Another gap, at least in some of the builds of it, it's missing create does, which is a bit of a gap. I have a version of that sitting in some of the branches as well. That's easy to implement as well on top of what Dr. Ting has put in place, but one to look for. Bunch of different things I've played with over the years. One I guess I'll highlight just because it's easy to throw up in the screen is let me show off Forth Haiku for those of you who have not encountered this. This is a variation on Forth that uses a floating point stack, and the reason is that it's intended to run on the GPU, and so a small program like this can produce a live animation. It's by no means a standard Forth. It uses each pixel of the resulting image is generated by running the program interactively. So let me give a little quick thing here. You have the X coordinate and the Y coordinate, and you can put them on the stack. And at the end, the expectation is that you have an RGB value there, and so you can produce images in that way. You can, for example, also include time as a component. And so if you say, for example, take the sign of t and add it in with x, then you can have something that see that folks other than myself have crafted all manner of interesting things. Someone impressively even generated Pac-Man, and there are all sorts of fun things that folks have done. Nominally, it's called Forth Haiku because the intention is to produce a very small program, which is, I think, one of the things that attracts me to Forth in general is simplicity. And so, oops, I've got apparently my search feature is down, which I will look into later. But there it is. Any questions? And hello.
Okay. Yeah, thank you very much. Are there any short questions to Brad?
It's a very different type of Forth, using the GPU to do the work. Makes me think about Charles Moore's idea of ultra-high Forth. his new implementation. Thank you.
Apologies, I think I lost audio just then. I missed the
way you're talking to the system using the GPU to display the information. That's very clever. Charles Moore did something with his new forth from color forth to ultra high definition forth. He's doing something similar like that using the GPU to do the work. Very clever. Thank you.
Indeed, yes. One thing you'll see with Haiku Forth is, unfortunately, it is heavily constrained by what at the time were the limitations of a WebGL shader, and so there's sort of limitations in terms of how much each. One nice thing about the Array Forth and Green Array's devices is that they offer a lot of flexibility about how neighbors communicate, but indeed, multiprocessing, I think, has a lot of fascinating directions you can take it, especially with simple.
Thanks, Brad.
Okay, yeah, thank you very much, Brad. Our next speaker saying hello to the group is Caesar Bloom.
He's not there, Ulrich.
He's not there, okay. So, which means we have the unnamed person who is also not there, and we're ready for the coffee break, which means we take 5 minutes break to have a coffee. And then I would say, yeah, we continue with Don Golding talking about FORTH for beginners, starting FORTH, the beginners class. And so the break will be 5 minutes. Is that sufficient? I think so. 5 minutes, which means it's in Europe, in Hamburg here, it's 5 minutes past 6. And which means whatever your time is, we meet somewhere at 10, 12, 12, or is 5 minutes? Yeah, 11, 12 minutes past the hour at your time. We meet here again. See you soon.
Thank you. Boy, it's gotten real quiet. Everybody's stuffing their face. Sorry. Maybe it doesn't work when the microphone is 3 feet away. Very quiet. Everybody eating. I'm about to eat. I got some food going in the oven.
Guys, can you hear me?
Yeah, you're fine.
Oh, great. So I just put this webcam in use today. I bought it like 4 hours ago and it seems to work. That's great news. Hi, Cecil.
On Linux, I use Minicom to talk to my board.
Cecil, Cecil, hear me?
Ya, estoy aquí.
Ah,
¿Cómo está?
muy bien.
Muy bien.
Tu
Yo
placa,
también.
your in the hardware you show use have video output?
No.
Only for terminal.
Two serial ports are on it. So the Unix that's available is the text-only version, which is fine. You know, it just compared to CPM, the Linux 4.9, which is what's available, is extremely rich in operations capabilities, subdirectories, protection, you know, all kinds of stuff that CPM doesn't have. But no graphics. It'd be interesting to have a 68030 board with some kind of graphic controller built in. But due to the health issues, that's the kind of stuff I like doing, designing hardware. I wouldn't have the time to do it. If I did, it would take me forever because a little bit every day until it's done.
Okay, only graphic
Tower
for
Hanoi.
terminal.
Yeah, Tower Hanoi.
Okay.
In a terminal.
You can do the Tetris game too. Born in terminal.
For years, I used Pygmy Forth, which is a text-only Forth. I loved it, but that's okay. The applications I wanted to build required only text.
Yes.
Interfacing to the network servers to get status of my servers and that kind of stuff, you know? Text only was fine. Didn't have TCP/IP, didn't have windowing, didn't have a whole lot of anything, just bare bones Forth. So eventually I developed my own libraries to do that. And I'm a big fan of libraries, not necessarily sharing libraries, because your Forth and my Forth, unless we're using the same thing, you know, we start using words that we added and therefore nobody else has them. So unless we include all that stuff, it's a one-person system, which is what Forth is all about. You tweak the Forth to be your language, you know, and then you can be very effective. And Peter, if you're talking, there's no sound.
We need to carry on with the class of Don. Sorry for the interruption.
Okay.
Where is Don? Don, are you ready?
Yeah, I'm ready.
Okay, then go ahead. So starting FORTH, the beginner's class.
All right, so I got a couple things. All right, can you see this screen right here where my mouse is?
We see the presentation. I don't see your mouse.
Oh, okay.
Yeah, now there it is.
Okay, so starting forth, focus on hardware development. You see that?
Yes,
okay.
Perfect, Don.
Okay, so I'm working with closely with Dr. Ting and Brad on, we're calling it the AI bot. And Brad has made a GitHub where the initial code is being stored for people to download. Is basically, we took Dr. Ting's, or Brad took Dr. Ting's eForth and is, modifying it so that we're going to include all of my my Triune OS, which is a robotics language for intelligent machines. And I had built Whiskers robots back in the 1990s and sold over 2,000 of them. And I built a very custom language for robotics, and that's where we're going with this. So what I want to do with that in mind, I want to use Dr. Ting's eForth, and we're going to teach Forth on that platform. So we'll use starting forth as basically the reference text. When we get into loops, we will, obviously Dr. Ting hasn't implemented do loops, but we will go over the do loop, but we'll also go over for next. So I'll be adding that, even though I'm using starting forth, and it's not in there, we'll be adding that to the presentation so that we include for next. So why Forth? I mean, Forth is an obsolete language, no one's using it, blah, blah, blah. Well, not true. Obviously from this group, you can see a lot of people are using it. I am an electrical engineer. I've noticed that 80% of the people that love Forth and use Forth are hardware guys. And it's because hardware guys know how a computer should work and how a language should work on the hardware. So yeah, I've seen a lot of hardware guys, that really get behind Forth. And so why is that? Isn't C the language of choice today? Well, this is why I like Forth. It's interactive debugging. So I do C for a living, I do embedded C. Well, if I want to debug something, I have to write code and I have to compile the code. I have to compile all my code, not just the one thing I changed. I have to JTAG the processor, I have to download this big binary block, and it may take me minutes, round trip. Maybe it's even 6 or 10 minutes if it's a big application. It could be on an FPGA, it could be an hour to compile it, C code for like an embedded micro on an FPGA. Whereas interactively, you saw in previous presentations today, well, I thought that was a great presentation earlier where the presenter, just did a colon definition, created a new word, and he's off and running. You can interactively ping and, peek and poke at hardware, and really important for debugging. Incremental compilation. C is you have to compile the whole thing, and you have to, like I say, JTAG it. Incremental compilation is huge. It's a huge improvement over every other language. There really isn't any other language that I know of that's incrementally compiled, except for maybe some of the AI languages that are implemented. I think maybe Smalltalk and Lisp might be, I'm not sure. But anyway, incremental compilation is a huge thing. My long-term focus is AI. I'm very interested in AI. AI and robotics is my current focus, but longer term, I want to do a lot of AI type of stuff. Do you think that when a computer learns something new, it has to recompile its entire self, right? Versus incremental compilation. The human brain is an incremental compiler, right? So Forth really maps to AI much better than any other language. We want our computers to learn incrementally and learn new things incrementally. We don't want to have to wait till we, compile the whole bloody thing and have to download it. It uses much less memory than compiled C for more complex applications. Peter talked about that, how he notices 3 to 10 times more efficient use of memory than a typical C program. I designed a teleradiology system back in the 90s, and that was really important. I'm going to go through that a little bit further in the talk, but when you use memory, when you're stingy with memory, it leaves a lot more memory for your application, for buffers and stuff like that. Forth doubles as your micro OS. No OS needed. You don't need an operating system with Forth. Forth is the operating system. You only need a computer to run a simple terminal program, i.e. like RealTerm on a PC or a Mac. You can use any computer. You could use your cell phone. You just need a simple terminal program. With the ESP32, Brad's got it working in a browser. So, I mean, anything you can have a browser on and, has Wi-Fi, you can talk to the ESP32, i.e. the robot. So the ESP uses Wi-Fi and, and also Bluetooth and the USB. You can program it using USB. Thinking Forth, when I first learned Forth myself, it was back in the 80s, and I had a copy of LMI Forth that I had acquired through a company, a high-tech company that I'd started, and it had failed, and I had this copy of LMI Forth, and I was very curious about it. There was no classes in Forth, so I went to a local university and took Pascal so that I could take the next course, which is data structures, and so Pascal was just another language, but data structures is, that's the art of programming, right? In thinking Forth, Leo Brody focused on the aspect of you don't write programs in Forth, you create a language for your application. You create a new language. So in my robotics, the new language is English. Forward 10 feet stop is actual code. And that's what you want to do when you use Forth as your programming language. Another key feature of Forth is always available. You may create all these high-level words that operate your robot, but Forth is always there, and you can always write new code. The user can write new code. It's not compiled. It's not a black box. So your application actually inherits Forth features of incremental compilation, of interactively, executing words and debugging. You create words using the English language. Don't be cryptic. Don't use computerese. Spell it out. Don't make it so that any human being can read your code. When you write Forth code, think of it like a non-programmer is going to use your system. Use words. Use long words. Memory's cheap. If you use English to create your words, you're automatically speech recognition capable. So, like I said, when I created my Forth language, or my robotics language, one of the things I did was I didn't want users to be, playing with the stack, right? Wrote, dot, swap, dot, all that stuff. So I created basically, I use variables to pass parameters. So we were talking, about earlier, it was about turning the lights on and off, right? So I made a comment to that presenter about, lights off or off lights. We should be able to support both. So we have a word called now that we put at the end, and now you can, if off and lights are updating variables, now can interrogate those variables and send the correct code out to the hardware. So if we start thinking in terms of using English as the programming language, then we're making our machines much more powerful and easier for non-programmers to use. And all you have to do is put a speech recognition front end that goes speech to text, and you can talk to your machine. Easy user interface. FORTH uses a serial RS-232 port, and most boards support USB. FORTH versus C. C must compile the entire application after a small change in source code. Then you must JTAG the processor using special tools with the entire bit file. You must create C functions for code hardware testing, increasing the size of your code. You need a fast laptop or other computer for editing source code and compiling. One of the things that C tries to emulate interactivity is using source level debugging, and it's very complicated. It's a little bit on the slow side. It does work, but you create watch lists, for your variables, so you can see what the variables are. It's very, very cumbersome. But it's better than writing your own, debugging code in C. And you may need an operating system. I do embedded systems programming, so I rarely use an operating system at all. I like to use PICs and that sort of thing. So I write bare metal C programs. But if your application may need an OS, so now you have this. If you need an operating system like Linux, now you need a way more powerful processor. You need DDR RAM. You need some sort of memory. So that greatly increases the need for hardware, and that's cost to your product as well. Examples of projects that I've done in FORTH: a teleradiology system I did in the late 80s. That was my first FORTH system. Basically, that was on an IBM PC. The IBM PC had 640K of memory, but it also had an imaging board that would take video and digitize a video image into memory that was on the video board itself, that was mapped at 64K window, mapped between 640 and 1 meg. So the board came with C software that would manipulate the image, and this is typical of C. Whoever wrote the C program wanted to paint the image from top down. So each part of the image, there was 4 quadrants, right? There was the first, the second, the third, and the fourth. What the guy would do is he'd paint a quarter, half the screen, half the line, switch blocks, and then paint the next one so that it would scroll down, which is ridiculous. So what I did was I threw away all the C code and I wrote it in FORTH. And what we did was we used an assembler instruction in the IBM PC that would do a block move at 64K. And so we would update an image in a fraction of a second, where you could actually see the C program paint the screen, to upload the image into the digital memory, the video memory. So there's an example. The entire program I wrote was less than 64K. So I also had the memory size was 256K for the video memory. So I actually had 2 buffers in in program memory. One was the pre-image buffer and one was the next image buffer. So when the user would press the left and the right arrows to go between the images, these are X-ray images for doctors, he'd tap on the key, and then in the background, so first when he tapped on the key, the previous buffer would be loaded into the video memory, and it would do it in a fraction of a second. So he's studying the image, and these doctors would typically study the image for at least a couple of seconds. Well, it took a couple of seconds to reload those buffers from the disk. So now it's ready for the next, tapping the key, either previous or next image. So this is an example of how Forth is far superior in controlling hardware. My Whiskers robot I designed in early 1990s, 1991, and I wanted to build an intelligent robot that was anthropomorphic. And so I developed a 3-level operating system, AI operating system that I'll go into in a different talk. That was very unique and allowed people to program the robots, more teaching the robot rather than programming the robot. I'll get into that in a different talk. I also developed the world's first man-packable robot for U.S. Special Forces. There was a lady, KG Engelhardt at the time, was running the NASA Far West Technology Center for NASA. And the idea was there was 4 of them around the country, and NASA was trying to get NASA's, developed technology out to companies to be able to utilize this technology that NASA was developing. And I met Colonel John Blitch from U.S. Special Forces. He had an $80,000 grant from the Army AI lab to explore the possibility of using man-packable robots. And I built the very first robot, which the military nicknamed Goldie, because it was a gold anodized 4-wheel robot that was invertible. It would fit inside a backpack, and that was the very first man-packable robot that the U.S. military used. Once they got money for this program, they got $50 million. John became program manager at DARPA, and then iRobot got all the money. So yeah, it's typical. I also developed an automated guided vehicle for moving boxes in a factory for a science museum in Georgia. So here's some of the robots that I've developed. The upper left is a man-packable robot that you see the big black knobs on the side. You unscrew those knobs and the sides come off, and then you could put that in 2 soldiers' backpack. The one just below it is Intruder, and I sold an Intruder to the CIA that actually went on a real mission. The brain there, that's the 3-level architecture that I developed. I'll talk about that in a future. And that's for controlling intelligent robotics. And that's basic, it was easy to do in Forth. It could be done in other languages, but Forth made it really easy. So you see the one robot off to the side there, it has a track on the top and it's got the black and yellow tape. That's my AGV, and see it follows the tape on the floor, and it has optical sensors on each side of the top there. You see that there's a belt on the top. So it would go from one conveyor, wait for the box to interrupt the beam. It would turn the belt on, grab the box, go to the end, and then drop the box somewhere else. Whiskers is the upper right, and it's a 2-wheel differentially steered robot. It could spin in place, so it's got a tail on the end with a caster. You can't see that. You see the optical sensors, those are LEDs and photo Darlingtons, and you could see probably about a foot away, and you can see the 2 whiskers coming off each side, which is where he gets his name. The lower right is a robotic kit I developed, but never got any interest in the tech ed market I was in. I sold over 2,000 robots. There was, I have a curriculum, and we're working on this new AI bot, which everything will be ported over to the new AI bot. I sold over 2,000. There's probably a couple of 100,000 kids over 10 years went through this curriculum and hands-on with the robot and learning. They learned forth. So this is a picture of my website back in the day, Angeles Research Corp. If you want to look at it, you have to go on the Wayback Machine. So the Triune OS, basically what I did was I had a foreground task, which I called the goal level. Background task was emulated the brain stem and your nervous system, and I called that the instinct layer. So you notice instincts, the priority is the highest, the intelligence is the least, it operates in the background. Tasks and behaviors and instincts are instantaneous reaction. There's no thought to it. There's no time component to an instinct. As long as a sensor is being activated, there's a motor override that's overriding and turning the robot in a different direction until the sensor stops seeing it. So that's the definition of an instinct. Tasks and behaviors. So every 10 times a second, from the ISR, interrupt service routine, which is the background, it would jump to this this task list, task/behavior list, and it would execute all of the forth words that are in the task list. Now, let's say that the goal level just says go forward. That's all it's saying. So if it sees something, the instinct would avoid it automatically. And so let's just say it saw a Coke bottle or something and it hit the left whisker, it would just instantly go around it. Wouldn't even think about it, wouldn't make a decision, it would just happen. So let's say that we have 2 Coke bottles and the robot comes up to it. What would happen with the instinct level? It would oscillate between the 2. So I needed a way to arbitrate that. So now that's where behaviors come in. So if I get a double whisker hit, this one gets hit, then this one, their 2 flags get set asynchronously, so they had different time periods, but when they're both set, that kicks off a behavior, which is a double whisker hit, and the robot would go back a foot, turn, go forward, and then get it back on course, and the behavior terminates. So by using these 3 levels, you can build a very intelligent robot. It's like teaching a child, if you're in this situation, do this thing. So we're gonna be working, the classes are gonna be working, you're gonna be learning forth, but at the end of the classes, we'll be transitioning into this new robotic system, which is this guy here. This is a new board I'm working on. And Dr. Ting has been waiting very patiently for this. So I got some time over the holidays to work on it. The future of Forth. So this is what I see the future of Forth: intelligent robotics, intelligent space systems, and artificial intelligence. These are very exciting areas for Forth. In my mind, Forth is the ideal language by an order of magnitude for these fields. And so I'd like to see the group, working on this. I'm going to be working on it. Let's see. So let's talk about space for a minute. I work at a company called Made in Space, and so I'm designing space robotics. I work as a senior electrical engineer there, but let's talk about the application of robots in space. I see Forth as being very critical in this area. Space, think of a probe that's out at Pluto. The comlink is very low speed. right? The RF signal has to go a very long range. So that drops the data rate. We need to be able to update software remotely, right? Are you going to upload, let's just say you write all your code in C, right? Okay, so you got this robot that's, let's say you got 100 robots on Pluto that are doing mining, and you have to upload new software. You change one line of code, let's say they're all written in C, what do you got to do? You got to upload this huge binary blob for each robot, and you probably have to have a microprocessor to manage the JTAG pin, the JTAG interface, to be able to reflash this processor in space.
Don, in C, it would be gigabytes of code.
Especially with 100 robots, yeah. It might take them a month to update these robots. So then, yeah. So I am nudging Made in Space to take a look at FORTH. They're not at the spot where they need it yet, quote unquote need. But I'm nudging people. I got a couple people. I have a few people actually in the software group that are interested. I think once the robotic board is done and I can show them how FORTH and robotics are a tight thing, they'll be interested. One C programmer, I gave an hour-and-a-half talk on FORTH to our software team one time, and at the end one guy says, "Are we really going to make our programmers, learn a new language? How many languages do each one of you guys know? You know one language? No, I know it, half a dozen or more. If you're a programmer, you get a new job, you're going to have to learn a new language. That's just part of the job. So I don't buy that one. Longer term, I love what Elia's doing, and a few other members of our FORTH2020 group. Big fan of FPGAs. I designed the space flight computer for the Archinaut 1 project at Made in Space, and it's just going to fab. So everybody pray for me that my board works when it gets back. One of the things I want to do is to build a new FORTH computer based on an FPGA, and I'll give a talk on that too a little bit later on. But this is basically what I kind of see the future of FORTH is. We have a FORTH command processor inside an FPGA. The RISC-V core, which takes a lot of resources in the FPGA. All our C guys, our C++ guys, can compile code on the RISC-V, but the high-level command and control is a FORTH processor implemented inside the FPGA, so that it will talk to the wireless command link, and that's how the program can be changed very rapidly by using FORTH as command processor. And then, of course, I do Verilog and VHDL, and you would write, some code would be written in that, obviously, as well. Okay, see if this is going to work. This is a little 4-minute video on Made in Space to give you an idea what I'm working on.
When I look back on the last 10 years for Made in Space, I really—
Can you guys hear the audio?
Legacy that the team here has started to build. We've been able to—
Yes.
functional objects in space for the very first time as humans. We've been able to do that commercially, which is its own quiet revolution.
We've had a lot of milestones in our first 10 years. With NASA, we built the first ever additive manufacturing device to go into space. Then we built a commercialization facility that additively manufactures in space, and that's the first and only up there. We were the first company to produce Z-Plan in orbit, and we're also kind of revolutionizing in-space manufacturing assembly with Archinaut. The progress with in-space robotic manufacturing assembly has been tremendous. We were looking at the 2030s when we start doing this on most roadmaps that you'd see. Both with our vision and the folks at NASA really pushing for this development, we were able to pull that timeline forward. And, we're going to be doing a demonstration here in 2022.
3D print was this huge media moment, but it's sort of like the nucleus of so much. Without the team learning there, we couldn't push in multiple really, really important and transformational directions. That technical demonstration allowed us to realistically say, what products can we manufacture on orbit? And then taking all that expertise and knowledge and pushing that to changing the way we design, build, operate space hardware for manufacturing parts of spacecraft and one day whole spacecraft on orbit.
3, 2, 1. We wouldn't be here today, and I wouldn't be sitting here without our great team we've built. Without them and their dedication, we really couldn't be where we're at. Without the buy-in of our customers, especially NASA, we wouldn't be where we're at.
There's this wonderful body of research that NASA has diligently done and continues to build on in material science regime that we've been able to look at and say, well, that's really interesting science, that's really interesting physics, and here's a business case, and marry those three things together, and now we're starting to really cook with gas in expanding the utilization of space. Over the next 10 years, I think we're going to see a shift in the way we do space infrastructure from sort of an expendable model to more of a kind of servicing. We're going to see the birth of the second huge legacy of the International Space Station, sustainable low forward economy. Using that space infrastructure to provide next generation capabilities to our customers on orbit, as well as delivering new products and services for the benefit of all humankind. And that's the core vision and thrust of Redwire. And we're super, super proud of being a part of that.
Being a part of the Redwire team now, it really expands our capabilities quite a bit. Just having that support from other folks that have been in the industry in different sectors for a long time really pushes what we're doing here really further along. And now we're going to be, as a collective, developing a platform that's going to be widely extensible to a lot of mission sets.
10 years ago, the public's attention on space was very, very different. And Made in Space has been the small but mighty part in changing the conversation, delivering the technical results to make that conversation an enduring one. And I'm really excited to see what, together with our partners and our customers, we're able to accomplish in the next 10 years.
Let's see. Hello. No. This is the program I'm working on. This is called Archinaut 1. I'm designing the flight computer. So it's 3D printing that beam for the solar panel, and it's unrolling solar film to create it's going to be a 10-meter beam. So it's going to be over 30 feet long on each side. So we can build extremely high power solar power systems right in space and take very little launch vehicle. We just bring up the filament and the rolled up solar film, and you can build huge solar panels in space. Okay, so yeah, here's where it's going to switch off between one side and the other. So the robot arm is going to pull the pin and it's going to grab, that's called the ESAM. And basically it's the 3D printer. So it locks the beam in space. it's going to grab it, puts it on the other side, and then it unfurls the beam while it 3D prints. Okay, so now I chose this board. Dr. Ting had a different board, but the robotic AI robotic board that I designed is using the pinout from this one. I don't know if the pinout is the same as Dr. Ting, so I would recommend that you get this board. They're basically $7 a board. You know, on Amazon, you get 2 boards for $14. They're dirt cheap. And so I would kind of recommend getting this one. Everyone that's wants to do the 4th class, you don't have to use one of these boards. You can download G4th and you can go through the curriculum and learn 4th without any cost at all. But these boards are really cheap. They come with even a USB cable. I think they do, or maybe you have to buy the cable. But you know, for less than $10, you can learn 4th on real hardware, and we'll be using obviously Dr. Ting's E4th, you know, for this. So one of the things I noticed when I learned 4th for the first time is I didn't really learn 4th until I had a real application. When I started, you know, flipping bits and turning LEDs on and off and that sort of thing, that's where 4th, it really clicked for me. So I would encourage you to do that. Brad, I'd like to see you maybe next January do a complete install, because you have to do the ESP32 plugin for the IDE. So if you want to do the AI bot, I mean, you want to do the ESP32 between now and January, buy some of these boards. You can use a different board, but just understand that you may have to change when I start turning LEDs on and off. It may be a different port. That would be the only disadvantage. But if Brad, maybe you could do a full, you know, step-by-step install of the ESP32 for folks before we start the class. That'd be great. There's my contact information, and that's my cell phone. If you guys want to talk, I love talking about 4th, love talking about stuff. So that's my contact info. Any questions? Am I still on?
Yes, you are.
Oh, good.
Don, just a dumb question. Early on was the discussion about the different versions of the ESP32, the Vroom kit, and I forget what the other kit. So that's the difference between the two, the pin connections.
Yeah, so I have not compared all the different pin connections. Peter talked about that in his talk. Yes. You can literally use any, you know, you can go through the course with any ESP, but you know, it may be, the pins may be mapped on different ports. You'd have to change that for your board, unless you you know, buy the specific board that I'm using on the AI bot. So I think it'd be a little easier if you bought the same board.
Oh, fair enough. Fair enough. Thank you.
It's really your choice.
Thank you.
And we will be supporting you know, for next, because that's what's in E4. So I have to shoehorn that into starting 4th.
Thank you.
Any other questions?
Don, is starting 4th for the next meeting? Are we starting with them? Okay.
Yeah, I'll probably take materials out of starting 4th and create a custom PowerPoint that's more tied to the board, you know, the ESP. But like I said, you can download G4th and you can learn Forth. You know, the focus is going to be learning Forth, not the ESP would just be a platform. So what I'll probably do is the first part of the class is going to be general Forth, and then the last 10 minutes I'll like apply it to the ESP. So if you get G4th, you're going to be supported in the first part of the course.
Don, we got here Francois Lager. Can you ask directly, Don? Use the opportunity you have to ask, or should I ask for you? It's no problem.
I don't know what your question is about, Peter.
About the ESP and the space.
Yes. Is it radiation hardened sufficiently to support space applications?
No, typical space applications is 100 kRad, and very few micros can, there are some that can do it, that can handle that kind of radiation. It turns out that FPGAs are excellent for, to make them radiation hardened, especially the flash-based microchip. Xilinx also has radiation FPGAs. So I think most people are going to FPGAs on their missions. Some people are using the rad-hard versions. There's a $2 million board out there if you'd like to buy one for rad-hard space missions.
Oh my God.
Yeah, 2 million. So the rad-hard, we're using an RTG4 for microsemi, and it's a very nice FPGA, and it's only 38,000 for one chip.
But Don, 2 million in NASA in California, but on Alibaba or eBay for $4. Come on.
Yeah. So and let me just say one thing about Forth in space. Forth has been very heavily into space. Chuck Moore designed the Shaboom processor, right, in the mid-90s. And the funny thing was, when he got a patent on the Shaboom, he did two things that he got millions. Well, okay, it's kind of a long story, but AMD, Intel, all the microprocessor manufacturers had to pay a business entity that Charles Moore was involved with. And he had two key things. He had one, he used a PLL to multiply the clock. These are just line items. They weren't the main patent. They're called claims. But he had a claim for using a low frequency external oscillator and bumping it up inside the chip so it could run fast. And then he had multiple instructions, per the width. So let's say is a 32-bit micro, and there's only you only needed 5 bits to point to a word, so you could execute up to 3 words in one clock cycle, in one fetch, right? So those two things, all modern micros do that now, and it's kind of a long story what happened. He's not a millionaire because of it, because somebody ripped him off. But anyway, from the Shaboom processor, he created another one called the RTX2000, which he did that in conjunction with Harris Semiconductor. This was at the end of the 90s, and later on it was called the RTX 2010. And if you put in NASA RTX 2010 or Space RTX 2010 in Google, you'll see a lot of missions use that micro even today, and that's a Forth processor. Somebody wrote a C compiler for it. So, whatever.
Can I jump in there at this point, Peter? A couple of questions from myself to Don. So first of all, Don, in one of your early slides, you had 3 fields, the third one of which is artificial intelligence, where you said you think Forth is ideal for. but then the rest of your talk was really about robotics. So I'd really be interested, given AI is quite a broad field, which aspects do you think Forth best suits? The second question I've got for you, Don, is the kind of standard text now for teaching robotics at master's level is this one by John Craig. I'm sure you've come across the gentleman.
I have a copy of it. I haven't read it yet.
Right. Well, while you were talking, I flicked through the chapter on robot programming languages, and it's really interesting. The requirements that Craig lays out are that the ideal robot programming languages would be great at managing a model of the world via geometries, great at specifying motion, being able to use events to drive flow of control. He talked quite a lot about how having an interpreted environment is massively important, as well as a compiled environment, and then sensor integration. So my question is, that sounds like a specification for Forth. So I know there are lots of great examples of robots that have been programmed in Forth, but they're a minority. I mean, C is much more prominent, and yet it has fewer of these features. So how has this come about that Forth is not the dominant language in
Oh, that's really simple. It's because academia is in love with C. C was created, by MIT and probably in conjunction, and maybe Dr. Ting knows this, or Bill Ragsdale. C was created in like 63 or something like that. Forth was created also at the same period of time by Chuck Moore for the Kitt Peak telescope in Arizona. He created Forth because he was writing everything in assembler language and said there's got to be a better way, a faster way. And he started looking at he was very much creating subroutine threaded assembler, and he started seeing a pattern there, and that's where Forth came. Charles Moore said he didn't invent Forth, he discovered it. I thought that was very prophetic. Getting back to your question on AI, our brains incrementally compile. Fundamentally, AI, if AI is gonna match our brains, it has to incrementally compile. So show me another language that does that. You could write it. You could write a new AI language in C and add an interpreter on top. But then, by the time you got done, you'd have a really complicated Forth. Forth is an amazing, language operating system. It's everything. And it's, all the high level languages like C want to keep you the programmer from touching the hardware. Forth, you're integrated with the hardware. You're there. You're right in the processor. As a matter of fact, the stack is the system stack on the processor. In C, the system stack is used to pass parameters from one function to the other, right? But you can't touch the stack. You can't touch it in C.
Don, the battle bots, everybody knows battle bots from San Francisco group, they started only with Forth. All the bots on the arena in the 80s was with Forth and with the chip from Motorola, or Rockwell 65F11, I think, or one of them from NM1.
Probably 68HC11. I used that in that's 60 micros, and I used that in my robot. Yeah, I paid $45 a chip for those.
I use it also.
Excuse me, there's one other reason why Forth is not so dominant. So even for the boards, the bare metal boards, nowadays you need a sort of board package where everything is implemented to initialize and so on. And for C, you just have the host compiler on Windows or Linux and nothing but that. If you say Forth requires is an operating system, and so this is right. So the automotive industry or the automation industry or the embedded devices, those companies don't want to run an operating system. If so, they want Linux. If they don't want, they want bare metal. And if there is no implementation by the few chip manufacturers like ST or TI and the other ones bought together, so there is Atmel still, whatever. If they don't implement for each even demonstration chip board for $30, whatever, a fourth engine, it won't work. The same problem is with Java or with Lua or with even Python. The boards had in the last 20 years just, let's say, 5 or 10 or let's say 8 or 16 kilobytes of RAM, and this was not sufficient for any kind of interpreter. So it's easier to have a C library which just sets ports somewhere in the RAM, which are I/O hardware, instead of implementing FORTH for a totally different processor.
You remember my screen, and it showed the FPGA and the FORTH at the top, and then the RISC processor, and then the fabric. So, you know, we're not going to go out and get everybody to change to FORTH. Ain't going to happen. There's way too much code for C. So what we have to do from a marketing perspective is we have to sell FORTH for its unique properties. And I talked about in space, you know, the low rate data links. So I really like the concept of FORTH in an FPGA, because FPGAs are not interactive whatsoever, you know. But by putting FORTH in there as the master processor, now an FPGA is actually interactive, incremental compilation, and you don't have to synthesize anything. These are huge benefits that no other language can support. So I'm really looking forward to working with Ilya and some of the other people in our group about it, FPGAs. That to me is the most exciting that I'm personally going to be spending time on in 2021. I'm doing it at work, so it's, you know, it's a no-brainer. I'm already developing stuff at work, so yeah, I think FORTH has a lot of opportunity. It's the pendulum is swung all the way to one side where FORTH isn't being used for hardly anything. I think it's going to be swinging back over the next few years, because we have applications between intelligent machines and space that need the functionality of FORTH, and there's no other way to get it. You know,
so is there a standard implementation for ARM CPUs, which are dominant for the last 15 years on the 32-bit bare metal market? And even then, if you have this